Now we are going to start the session. Before going to the start the session, uh, I will introduce our today's speaker, Dr. Monzur Imteaz. Professor Imteaz is the head of the Urban Environmental and Transport System within the School of Engineering and Director of Masters of Engineering courses at Swinburne University. He completed his PhD in Environmental Engineering from Saitama University, Japan in 1997, followed by postdoctoral research at the University of Queensland, Brisbane. Throughout his career, he has worked with prominent institutions, including the Institute of Water Modeling, Bangladesh, Bangladesh University of Engineering and Technology, Queensland University of Technology, Brisbane, and Queensland Centre for Climate Applications. His research spans sustainability, water recycling, pollutant transport and treatment modeling, decision support tools, and rainfall forecasting using artificial intelligence. Professor Imtiaz is recognized among the top 1% most cited scientists globally in environmental engineering for 2022 to 2023. He is the author of the book Urban Water Resource and serves on the editorial boards of Resources, Conservation and Recycling and the Journal of Hydropower. He holds a PhD from Saitama University 97 and a Master's from the Asian Institute of Technology 94 and BSc Engineering from Bangladesh University of Engineering and Technology 1991. His work contributes to critical sustainable development goals, particularly climate action SDG 13 comes under and clean water and sanitation SDG 6. With extensive academic and industry collaborations, Professor Imtiaz continues to lead research and education to address global environmental challenges, fostering innovation and sustainable solutions for future urban and transport system. So now I'd like to call Professor Monzur Imtiaz to start this session. Sir, I'm handing to you, sir, for the session.
Okay, thank you. Thank you for your introduction. Good evening. And here it is 11:30 in the night. So for me, yeah, not first time, probably second time or third time in this late evening we are doing some presentation. But anyway, thanks for inviting me and giving me this opportunity to talk in front of you. And I could see lots of participants. That's good. That will make me awake, although I had a cup of coffee so that I can keep myself. Usually I don't take a cup of coffee in the evening, but this evening I had to take one so that I can keep myself awake. Okay, the introduction was given already by the facilitator, but I did write some stuff about me, but I will quickly go through this already mentioned by the facilitator. But basically, I'm teaching at Swinburne University since 2007, almost 18 years, and I am the head of Urban Environmental and Transport Systems. And some of my achievements, I was awarded this Vice Chancellor's Award on Sustainability. So today the topic is sustainability, and you can imagine I was awarded this Vice Chancellor's Award in 2008. Then I was awarded this Teaching Excellence Award in 2015. And also my book was published from CRC Press USA, which is one of the top publishers in the field of engineering. And also it was mentioned about, so basically I am the author of one book, one edited book, 24 book chapters, and 227 journals, mostly Q1 and Q2 journals. And I have completed supervisions of 20 PhD students. And also about my citation records, already it was mentioned. I am top 1% most cited scientist in the world. Yes, like in the international databases, I have got 368 publications recorded in Google Scholar and 219 in Scopus. My H index in Google Scholar is 43 and in Scopus is 38. And these are some of my credentials. Also, I'm serving in the editorial board members in that first one is one of the topmost journal, Resources Conservation and Recycling by Elsevier. I did deliver 7 keynote speeches in international conferences, and also in the international area, I was the grand proposal assessor for European Science Foundation, Government of Netherlands, France, and Kazakhstan. Anyway, we now get into the today's topic about the sustainability. Basically, this is the good one about the sustainability. You might have already seen, they call it sustainability compass. Although compass, we know that it should be north, south, east, west, but we change it. North is to look after the nature, south is to look after the society, east is to have balanced economy or good economy, and eventually west is w is for to have to improve our well-being. So this is basically the nutshell of sustainability. We need to balance all these four. In the past, they would not bother about the nature or you understand, but now we have to make a good balance among all these four um, aspects. So this is basically the sustainability concept came up from these things. I'm not going in details. Basically, the problem was, if you go back to 1950, 1970, the problem was not prominent or nobody bothered about this sustainability. But as population increasing and increasing, in this chart, you can see that number of mega cities, this violet color, purple color one is the number of mega cities, that purple colored one. In 1950, there was 0 mega city. Mega city is the one which is having more than 10 million population. And by 2000, we had already more than 15. And I think couple of Indian cities also included in that 15, couple of Indian cities. Then they are projecting by 2030, it will be 29. So why we are talking about the mega city? Mega city is the big population. The demand is also quite high, and to fulfill that demand for energy, demand for food, demand for building, accommodation. So to fulfill all these demand, this is putting huge pressure on our resources. And while we have got this big pressure on our resources, we are trying to extract more and more from our limited available resources, and that's causing these environmental problems. And I'm not going in detail, but just some basic touch on that. This is the our sort of current energy demand in different sector. The demand for the coal, the bottom one, the middle one, demand of oil and demand of gas. You can see after 1950, it was increasing sort of exponentially, and that sort of exponential increase is quite sort of alarming for all of us, for the world. So this pattern is not at all sustainable. So then the climate scientist, they thought that we cannot keep going like this. We have to change to some renewable sources, and that renewable sources and we have to be sustainable in all aspect. So today I will be mostly, and that the economy and energy, all the countries, they are trying to increase their economy, develop their economy, which is good. Everyone should try and try to improve a lot. So if you can see this good relation between the GDP per capita in the x-axis, GDP per capita, which is the indication of the economy. India is sitting here, somewhere between the higher level, the highly developed countries, and then the low developed countries. So you can see all those, the developed world having higher economy, they are all higher consumption, in the higher consumption of energy. All these, Saudi Arabia, Norway, US, Japan, United Kingdom. So if we are like developing our economy. At the same time, we are consuming too much energy, and that's the problem. And this is again transport related greenhouse gas emissions. Transport related greenhouse gas emissions. You can see the largest portion is coming from the light duty vehicles like our car, and then not much with the two-wheeler or three-wheelers on the top. Not, but it has been increasing. It has been increasing year by year, and it will. The trend is quite alarming trend. Uh, Now, again, the climate impacts like carbon dioxide emissions per passenger. You can see per passenger, the airplane. I think some. Are you trying to send some message? Okay. Uh, I go back to my presentation again. Okay, so then this chart is showing the carbon dioxide emissions per passenger. So air travel, we can't really avoid. We do it for dire needs, but this car travel, which is quite, we can try to minimize. Even the two-wheeler, if we consider per passenger, forget about Hyderabad, because in Hyderabad I saw, I think even whole family in one uh, scooter or one motorbike, even whole family with the three kids, husband, wife. I saw in Hyderabad. So in that case, it will be really efficient. It will be really efficient in Hyderabad or in some Indian towns. I was a bit surprised to see like five people sitting in one motorbike. That is really like sustainable practice. Anyway, so now as a civil engineer, our contribution, the mechanical engineering, electrical engineering, they are trying to do a lot in that aspect. They have developed the electric vehicle, hybrid vehicles. So of course, those electric vehicle, hybrid vehicle, they can, they are sustainable. They can save, reduce the carbon emission. Although prices are quite high, in Australia, you can see some cars. But I remember I've been to Japan, I think about 12 years back, 13 years back, I went to Japan, and I was surprised. 13 years back, more than 50% cars on the street, on the roads, I have seen are electric vehicles. It was 13 years back. I think by now it has improved a lot. As a civil engineer, this is the town planning issue. Here, they are saying that we should not focus only one city center, which was the tradition. And I'm sure even in Delhi, in Hyderabad, one city center, in Australia and in USA, everywhere they used to be more dependent on one city center, all the people rushing to the city center. That was not really sustainable practice. Here, this circle here, this circle with the blank space, not the solid surface, solid circle with the blank space in the middle is the main city center. But what they are saying that we should have several sub cities or transit cities like these solid, big solid circles. So here there are 1, 2, 3, 4, 5 sub cities, and each sub city will have the good connection with the main city. But people from the surrounding suburbs, they will be dependent on this sub city, not the main city. And that's what. So then by this way, it can reduce the pressure on the main city. It can reduce the travel requirement for the people. So not 80% people, 90% people need to go to this main city center. Rather, they will be traveling to this sub city. And in Australian cities, they have started establishing this sort of sub cities. I am from Melbourne. In Melbourne, the government has decided 12 sub cities, and they are developing those sub cities like a city. So these transit cities will act like a main city center, so that people will not travel more towards this main city center. So in terms of planning, our civil engineers, they can contribute a lot to establish this sort of sub cities or transit cities. So that's what our contribution comes. Apart from that, like as I said, electric vehicle and other stuff, usually not really civil engineering job. Other people working a lot on that, so I'm not covering, but still some, you can see the difference. A typical Toyota Camry consumes about 8 liters per 100 kilometer, whereas a Mitsubishi Mirage uh, 895 kg, it consumes only about half per 100 kilometer. With the size and with the hybrid vehicle, again, these are some typically 50% fuel efficient in urban uses, 50% fuel efficient, the hybrid vehicles. So nowadays, many people, they are going for these hybrid vehicles. And then the electric car, again, becoming more common. Only thing that apart from your house, so house should have that charging facility. And Australian government, they are establishing in the motorway, they are establishing many these charging points. That is the issue while you are traveling. If your charge gone down, you need to charge your car. So that was the main issue, but government is doing, many governments, they are trying to develop in that sector. I'm not going in Australia. That sort of electric scooter is very widely used, and they are just sitting in the roadside. They are just, you can find it in the roadside, sitting in the roadside, and you just go, and from your mobile you can pay. From your mobile app you can pay, you can get the number of that particular bike, and from that number of that particular scooter you can pay through your app, and then you can just take it and you start riding it. Many people, especially the young generation, they are using a lot this sort of e-scooter, electric scooter, very efficient. And nowadays the uses are going to increase more and more. Mm, Now, basically, as my expertise is water and environment, I will be focusing, diverting now towards water. I just gave a bit of background on transport sector, not all, because that transport is not really my expertise, or as a civil engineer, we only can be involved in that sort of the city planning. And now I am focusing to the water sustainability, which is one of the major issue in the current world. And there are many innovative ideas. Many people, they proposed many innovative ideas. I'll go through some of those, and I did publish lots of paper in these features. Some are very basic, easy to install and cheap, however, only limited to some specific topography, and production also very small. So I'll go through one by one, a few of these one by one. This is called fog collection. In some geographical regions, they use this sort of simple device to collect the fog, and eventually fog is collected on this net, and from the net it is diverted to this container, and you can collect from this container. This is a sustainable approach, but not all the regions can have this sort of fogs, or not all the season, not all over the year. And collection amount also not great amount. It can really supply to some extent, but still going on. I have got I think I've got one journal paper on this, very good journal paper in that journal, Resources Conservation and Recycling. Then they call it solar steel. Again, especially in coastal areas, they use this sort of, you can use, and the generation is also, water generation is not bad. They use this sort of like container where through sunlight the saline water. So because the coastal area, you can easily get the seawater and put it there, and it's seawater, saline water will be evaporated during the day, and when it goes to the surface, then the condensation will happen, and then you collect it from the other side. If you make your top surface like this with a slope, you can collect it from the other side, and eventually distilled water will be collected in this container, which is quite uh, clean. I have got few papers on this solar still. Uh, then the other one is atmospheric water generator, which, like in this previous one, we said that fog collection and solar is this solar steel is using the saline water, but this one you can collect from the atmosphere, and then you use some sort of artificial cooling. In those one, you don't use artificial cooling, but this one you use the artificial cooling, and that artificial cooling you use from battery or using the solar energy. So to make it more sustainable, either you use battery or the solar solar panel to apply for that artificial cooling, and you can generate from the from the humid air, you can generate water from your atmosphere. Again, collection is probably not much, but still you can get some certain amount depending on your humidity in the air. I have got one journal paper on this. If anyone interested, I can supply those. Those are all in my. You can get it from Scoopus or even from my university profile. You can get it. Mm, Now, this is the large scale desalination. Just one picture of large scale desalination. In Australia, we had drought about in 2009, 10. We had big drought, 8, 9, 10. And then Australian government, they spent billions of dollars, not million, billions of dollars to establish, because like copying those Middle East countries, most of the Middle East countries, they don't have any suitable source of water. So they depend on this sort of desalination plant. So Australian government in those days when we had the drought, they call it millennium drought. And in those days, government had to spend some $1 billion to establish to this sort of desalination plants. They did establish, but the problem is, but how you run this desalination plant with the electricity, it consumes lots of energy and lots of electricity. And if your electricity coming from unsustainable source like the coal energy, then you are not really sustainable in that aspect. You are producing sustainable water through saline water, but to produce that sustainable water, you are depending on unsustainable energy. So that's the big question mark for this sort of desalination plant. And on top of that is having huge cost burden. It has got huge environmental impact, and that's why it has to be used only as a last resort when you don't have any other option. This picture was taken from Brazil. They had the similar scenario, the drought, when I have visited them in, I think, 2010, 11. They had the similar drought scenario. Now, this is the our magazine, like Institute of Engineers, Australia. So they have got this water engineering magazine. They publish it every quarterly. They publish it, and in that magazine they publish this article, the desalination debate, and the question they were asking: were the plants a good idea? Whether making those plants, the desalination plant, was a good idea or not, that was the question mark. And they wrote in details on that. I'm not sure whether you can read. They wrote here that in those days, the government, Australian government, they spent $18 billion, $18 billion to establish those desalination plant. But now most of the plants are sitting idle because those drought period gone. We are having now sort of enough rain, So most of those desalination plants are sitting idle. not producing water, but even they are sitting idle, there are huge maintenance cost, and because of those maintenance cost, that maintenance cost also quite large. So that's why they are now questioning whether that was a good idea or not. Anyway, that's we are not going into that debate. Now in Australia, we do have many new suburbs. In the new areas, we do have two supply waters. You can see two taps. One is normal one, other one is this purple color. In the new areas, they are putting two supply. One is normal supply, water supply, you can drink it. Other one is recycled water. And that's why they put this sort of warning sign, and they take away the tap head. You cannot, kids cannot use it because this water is not safe to drink. So they use that water for the gardening or toilet flushing and gardening. Because in Australia, most of the houses they have got their gardens in front of, in the front yard, in the backyard they have got some gardens. So you can use that water for the garden, but not drinking. That's what they do. They take the tap top, so that by mistake the kids cannot start using it or drinking it. uh, Although there is a warning sign there, but in Austria nowadays it's widely, they are widely using this thing. I did deliver a lecture in USA, and when I have shown this thing in USA to, I think, 2014, and they were surprised because they did not have this sort of thing. I forgot that. I think that not 2014, much before. Anyway, now if that recycled water is managed by the authority, you need to provide this separate supply system like this one, separate supply system that cost the cost burden and maintenance burden for the authority. And another issue for that thing is community acceptance. Community really don't want to accept that sort of recycled water. They don't feel safe, and safety concern also there. As I said, that's the reason in Australia they take away the tap head so that the kids cannot use it. And then usually, from the Melbourne city. This is our typical water uses pattern in household. 35% water is consumed for the garden, and 19% is consumed for the toilet. Now, with that consumption pattern, they said, yes, that water you don't need to be it doesn't need to be clean water. It doesn't need to be a potable water. It can be a recycled water, which is more than 50%. So from the remaining water, if you collect from the remaining water, uses bathroom, laundry, and kitchen, then that you can supply that water with some minor treatment or basic level treatment. You can supply it to the garden and toilet. And in Australia, it's happening. It's like every household, they are trying to, not every household doing, but there is option. So I'll show you a picture. So in the household, you can use some basic level treatment, and in that basic level treatment, you can collect from your bathtub, your shower. This is the shower, and your bathtub. You can have some basic level treatment, and then that can be used for the garden. Here is showing that blue pipe is used for the garden. The blue pipe can be from the blue pipe. They are using it for the toilet here. From the blue pipe. Blue pipe means recycled. The first recycled water I have shown you, that was for the authorized authority managing that recycled water. But here, not the authority. Every household they can do it. And you see, washing the car from that blue pipe, and in the toilet from that blue pipe. So that sort of things happening in Australia. Not widely used, but still, because there are some maintenance and treatment issues, some safety concern as well, and the most important is cost and payback period. People are not much encouraged when they consider about these payback periods. That's why I did some studies on that payback period. So if it is like multi-storied buildings like you have got in your cities in India, what they have found that you can collect from your laundry, you can collect from your shower and wash basin, you can collect it, you can do some sort of uh, basic treatment. T is for treatment, and then using some pump you can uh, gray water, that gray water can be supplied to your toilets. So basically, because your toilet demand is not that high, so you don't need to collect from every floor. You can collect from some floor, and the collection from those some amount fraction of floors. Suppose you have got 10-story building, you don't need to collect from all the 10-story buildings. You collect from few stories, and you can fulfill the toilet demand for the all the stories. That's what showing here. This GW is for the gray water, CW is for the clean water. Now we have done some studies for Dubai and for Melbourne, and we have found that we have tried to find out that relationship, that if you building is 30-story building, then you need to only collect the only about say 13 or 14 levels. You don't need to collect from all the 13 levels, all the 30 floors, and that's the way you can reduce your plumbing cost. If you start connecting collection from all the 30 floors, your plumbing cost will be quite high, whereas you don't need, because your demand of that gray water is not that high. That's why if you want to establish that sort of thing, implement that sort of thing, you need to use that sort of calculation, whether you need to collect from all the floors. Basically you don't need to collect from all the floors. And if you are using collecting from all the floors, you are like oversupplying and your cost will be high. So I did few studies on that. And also while we are doing that sort of payback period analysis, we have seen the payback period will be going down if we are using more number of floors. If you are using for the tall buildings with the many number of floors, then you can reduce your payback period. Here, the blue line is for Dubai. You can see your payback period is quite low compared to this pink line for Melbourne. Why? Because in Melbourne, or in Australia, the labor cost is too high. So for those plumbing and maintenance, you have to pay quite high amount of labor and plumbing cost and all these costs. Because of that thing, it is very difficult to achieve a quite a bit low payback period. While in Dubai or some other countries where the labor is quite cheap, I think India will be also even lower. You can easily you can get that payback period quite low. And if it is less than 10 years, payback period is quite good thing. Now the stormwater harvesting is among all the recycling options. This one is most feasible in many parts of the world. Why I say many parts? Because where if you don't have any rain, if you don't have enough rain, what's the point you are having that sort of stormwater harvesting? But in many cities, you do have that sort of good amount of rain, especially I'm sure most of the Indian cities. I'm originally from Bangladesh. In Bangladesh, you do get huge amount of rain, and this stormwater harvesting is simple, less expensive, no severe safety concern, because the stormwater collected from your roof usually is clean, and when the water is sitting in the tank, because of the settlement, most of the debris and most of the pollutants, they get settled at the bottom, and they collect the water from little bit top. Like if it is your tank, look at me, if it is your tank, they will not collect from the bottom of the tank, they will collect somewhere a bit high level, so that at the bottom some debris or some other pollutants can be settled there, and you are collecting little bit high, maybe about say 300 or 400 millimeter above so that you get relatively clean water. In some remote areas, they drink it even. Maybe you can do some treatment, boiling treatment, some basic treatment. You can drink it. In Australia, widely used nowadays, and government is sort of imposing onto the residents to, like, this is for a single house. That picture, I think I have got some more. This is for a single house, that sort of tank, and government will not approve your building unless you achieve some sustainability score. They come up with some score. So if we don't achieve some sustainability score, that score is like using less energy, having some natural light provision, having some natural heat provision for winter. So this sort of feature, you get some point, you get some score. And if you have this sort of rainwater tank or recycling option, you get some score, and your building permit will not be approved unless you achieve some minimum score. So that's the good things. Not only in Australia, many other countries they are doing that. You need to achieve minimum sustainability score, and that having the rainwater tank also gives you some score. That's why it is widely used in many especially the new houses. And government was giving some sort of subsidy. Suppose this tank was costing say $2,000, just for an example. Government was subsidizing it by paying say 50% or 60% of that money. At the same time, it is reducing your water bill. That water you can use for toilet flushing, you can use for garden, you can use for even for your laundry. So it's widely used. Apart from that house level use, some bigger scale also happening, some bigger scale. And this is the Australian map. I did some study for, this is the location of Sydney, the most famous city in Australia. I did some case study for a golf course. So this golf course quite big. I forgot the area, but quite big. And for that golf course, for the grass, they want to maintain the grass. They needed the huge amount of supply water, huge amount of supply water. So what the authority came to us, they were thinking why we have to use that much of supply water. Rather, they had some small ponds, like a small pond here, one pond here, one pond there. They wanted to enlarge that pond, and they wanted to collect the whatever the rainwater coming from this golf course area or from the surrounding area. They wanted to divert it all in these ponds, while these pond volumes are enlarged, and they wanted to use that pond water for the irrigation for these grass and for all these plants. They have to maintain these grass and plants. So they came to us to do that study. I did that study, and I came up with this, that if we keep on increasing the storage volume for those ponds, for those two ponds, if you increasing how you're like, this is called total water deficit. What does it mean? Even you are using those ponds, you cannot fulfill the total demand of water. They call it crop water demand. Crop water demand, you can't really fulfill the total water demand of those plants and grass. So still you will have some deficit, but you can fulfill some amount. And here we are showing those deficit amount. Now you see these things, when they implement this sort of stormwater harvesting, many people, the common practice, they don't consider this sort of dry year, average year, and wet year. And you can see distinct differences. These amounts here, 14 times, say this 14 times 10,000 meter cube. So like here, about 11 times 10,000 meter cube. This is total water deficit. So if you keep on increasing your storage volume, so the red dots are in the wet year, you can still reduce that deficit amount, you can reduce significantly. But after some time, it will be like stable. Even by increasing your storage volume, you can't reduce that deficit anymore. For the dry year scenario is quite different. From the very beginning, you can't really reduce your deficit amount because dry year, that collection in your pond is not much anyway. Collection in your pond is not much anyway. So you can't reduce much of your deficit. Now, the authority, they should, before implementing for that sort of project in increasing the volume and diverting all the water to these ponds, they have to do this cost benefit analysis. So they need to consider this sort of dry year benefit, average year benefit, OATR benefit, and that sort of distinct variation. It is more getting more and more important nowadays because of the climate change. The we call it variability. Climate variability is getting more and more significant. Climate variability is getting more and more significant in many parts of the world. So the users, they are in doubt. Even I install rainwater tank or I do this sort of thing, how much really it will give us benefit. Many people, we did some survey and we found many people, they are like in doubt. So we need to give them the correct scenario, the correct the outcome, the correct benefit. Unless you do this sort of analysis with distinct years, dry year, average year, wet year, you don't really get the correct scenario or the accurate scenario. I will show you some more. We did so. Now this is the average daily available water. So if you keep on increasing your catchment area, this this is in the dry year. If you keep on increasing your catchment area, it will give you more benefit. But if you increase more, you have to do more diversion to the ponds. So that depends on the available pond volume. Again, it scenario is quite different in dry year, in average year, and in wet years. I did another case study in Melbourne, in my university campus. What they did, this is Melbourne, right at the bottom. Sydney was here, and this is Melbourne, two major cities in Australia. Now, this is our campus, my university campus, a part of my university campus, not all the buildings showing here. Anyway, so in this area, they installed two underground tanks, big tanks. I'll show you the volume. One was 185,000 liters underground here. You will not feel it, it's underground. And another one is 110,000 liters here in this location, the big tanks. And now I did some analysis for these tanks, and they are connected with the roof water, storm water coming on the roof, and they are connected to these tanks. Now, the few buildings they have connected, not all the buildings, few buildings they have connected, and I did even after connection to this rainwater tank, and you are using these rainwater tanks for your garden, and in some cases toilet flushing, still you have to use some town water like normal water supply, which is like normal potable water, drinking water. So, but you see, in wet year, your your that cumulative town water use for the whole year. This is for the whole year. So in the wet year, you don't have to use much, only about here, only about 100 kiloliter. But in a dry year, these blue dots, which is about for the same uses, which is about 450 kiloliters. So almost more than 4 times of wet year. So you can see the difference between a wet year and the dry year. The supply water use, like even you have to use some supply water to augment the water supply, but that demand is more than 4 times compared to a wet year. The yellow line is for the wet year, and the blue dots are for the uh, dry year, and the pink one is for the average year. And you can see the distinct difference between these years. And then water savings. In one of the tanks, again, this yellow is the wet year, huge difference between the wet year and dry year, huge difference, more than, I think that difference is more than 5,000 kiloliters, more than 5,000 kiloliters. And on the other hand, because they have not done proper analysis, one tank is overflowing, so this figure is showing overflow amount from that tank because they have connected more roofs, but the demand from that tank is not that high, so eventually is overflowing even in dry years. So when we establish that sort of rainwater harvesting, we have to do this sort of analysis. If I don't do the proper design, then eventually I might lose some water as overflow. That's what in this case happening. One of the tanks, not both the tanks, one of the tanks is overflowing huge amount, which could be reduced with the proper design, and then which then connection we did not need for this tank. Basically, we did not need to connect with the many roofs. They have, as I said, they have connected with the many buildings, few buildings. So maybe we could reduce some of those connection cost. And this again, the payback period analysis I have done for those tanks, and I have found if our water price, we don't increase the water price, then the payback period would be quite high, and nobody likes to have that sort of payback period for above 40 years. So this is another issue. Our water cost was quite cheap those days, and it was quite cheap. So I have done this analysis. If you keep on increasing the water price, how the payback period comes to an achievable level or to some good level. Although people would not like to have their water price increasing, but still we have to come to some sort of balance. Okay, now these are again this household connection, quite a big tank. This is connecting two houses. This tank is connected to the two houses, you can see. Now, what was the usual practice for this sort of rainwater tank design? They used to consider long term, like 40 years rainfall. And from the 40 years rainfall, they used to get some average amount. And then they used to say you can save that much in that sort of tank. You can say, so they say take for 40 years data, and they calculate the water savings in 40 years, and they divide it by 40. Then they say average per year you can save that much amount of water. Yes, to some extent, but as I said, that this is one of my co-researcher. He did some studies for different cities in the world. I think he did about 14, 15 different cities, including Berlin, Paris, New York, Barcelona, and he came up that potential for portable water savings. So each line is representing one city. So with the increase of tank size, you can save that much water. Keep in mind, look at my heading. I am saying traditional practice. That was the traditional practice that they used to come up with one line for a particular city. But I am saying this is wrong. And I did counters. He is one of my co-researcher. I did counter one of his study, and I did show that this is having one smooth line for a particular city is not really accurate, not really correct. Uh, Not really correct, because this will be misleading, because they got, even for the large cities like in this one is he has done for New York, Moscow. They are quite big cities. Berlin. For large cities you don't get a single line like this. I'll show you more. So I have done some studies. This is for Melbourne. This with different roof area, how it behaves. This red line is for central Melbourne in a wet year, central Melbourne in a wet year, and this black line is central Melbourne in dry year. So you can see big difference between a dry year and wet year. This is water savings. And again, this gray line is wet year in North Melbourne, northern Melbourne in a wet year, whereas this red line is wet year in a central Melbourne. So within Melbourne, you can see the difference of more than 10,000 liters. Again, for this bigger roof, about yes, more than this one, difference is about more than 20,000 liters between within a city. Within a city, that sort of difference in water savings you can get. So if you show only one line, sort of misleading to the people. So this is the Melbourne map, and I have shown the spatial variability. These were published in few journals, especially in the Journal of Resources Conservation and Recycling. So I have shown how SE is the southeast Melbourne, central Melbourne, northern Melbourne, and southwest Melbourne. And you can see this is the reliability. Whenever you are using that tanks, rainwater tank, you are expecting to use for some gardening, for toilet flushing, but then there is another term called reliability. That reliability is basically number of days your tank is able to supply intended demand in a year, in a year of 365 days. So that's called reliability. So you can see with the increase of tank size, the reliability can be increased up to certain level, up to certain level. Then that sort of reliability can have huge variation as well within a city here, like 4 different locations within a city. That's what I have shown here. I have taken, sorry, I have taken 4 locations in Melbourne. This is the Melbourne metropolitan area, and I have shown that huge differences also in terms of reliability. Now, one of my friend also, I did write few papers with him. He wrote this same, published this in for Sydney, and again for Sydney, he for the different tank sizes, he came up with the annual water savings for different each line representing for a particular tank size. Like this bottom one is 10 kiloliter tank, and the top one is 100 kiloliter tank. He done this study for like multi-storied buildings, multi-story buildings in Sydney. Again, I do strongly differ with that sort of single line for a whole city, and single line for all the weather or climates, because climate do vary a lot from year to year. So I do strongly. He's my friend who did this. Rahman, he is my friend. He did this study, but I sort of disagree with him, and disagreeing on that, I did publish few papers. You see, in even in Sydney, this was for Sydney. My previous variation was shown for Melbourne, but this one is for Sydney. So one location is called Bankstown. So this blue line, this is cumulative town water use. The blue line is for Bankstown, and this green line is for blue line is for the dry year, and the green line is for the wet year. You can see big difference within Sydney, big difference. And again, this brown line is for the dry year, and this in another area, Lucas Height, and this is this is within 2 locations, the big difference. So with this sort of spatial variability and the climatic variability, I do have some more. Uh, I came up with this, and I was like emphasizing that we should do analysis for 3 climatic years, and then we should come back to some average, so that the users, they have some clear picture of what they can get out of all these uh, rainwater tank. Otherwise, people are not really convinced. People are confused how much really they can save. So that's why I did develop this software. The software name is eTank. The software, if you insert all your like tank volume, daily rainwater demand, some loss, and the connected roof area, and you provide 3 years of data. You provide 3 years of data. One is dry year, one is average year, another is wet year. So then it does analysis for you, and then you can do, it can calculate cumulative rainwater used, cumulative overflow, cumulative town water used, and also it will calculate the reliability for you. Reliability is in dry year, in average year, in wet year. It will give you the reliability values. So suppose you find some loss is quite high, you want to reduce your loss. Okay, if you want to reduce overflow loss, then you have to increase the tank volume. If you have to increase the tank volume if you want to reduce your overflow loss, or if you want to increase your savings, if you want to use your reduce your town water use, then you have to increase either the tank volume or the roof area. And also with this software you can do the cost analysis, which is the most very important. And if you do the insert the cost data for the water price, for the tank construction and maintenance cost, and this cost will be increased over the year, so that sort of increment rate. And then you can calculate, this will show you the annual water savings. And if you press this button payback period, then it will show you the payback period for that particular tank size, so that you can sort of design your own tank, the tank size, or how much roof you want to connect. Because if you want to connect the bigger roof, then more plumbing needed, more cost, which you want to minimize, which you want to optimize. So basically this software is for our mainly for our optimization of the tank sizes, optimization of, so that you don't end up having a big tank but you are not using that much water, or you are connected to a big roof whether you don't need to connect for that big roof. So you can really do this sort of cost optimization individual household level, and you can do your size optimization. Because land, if you are putting the tank, especially in Australia, they put this tank above ground, on the ground. Now on the ground, that much space you are losing. So now the land is not cheap. People also concerned about that, how much they are spending on the land. So that's another factor why people are not willing to use. So with the use of this sort of software, you can optimize your tank. This tool originally was developed for the end users. Yes, lots of people, they did take from me, uh, and there were few PhD students. They did lots of work. I think about, I forgot, I think one, two, three, four PhD students and master's students. They did use this tool, and they did lots of studies using that tool for different cities of Australia. I forgot. I think with that tool, only with that tool, using that tool, I did publish about 18 journal papers. I did publish about 18 journal papers, which used only this tool to produce different types of studies and different types of analysis. So far, yes, I think it was about 18 journal papers. Uh, and that tool eventually gives you that sort of three pictures. This one is cumulative rainwater use in dry year, average year, and wet year. So you can really do that sort of optimization, or you can play around with this tool. You keep on changing your parameter, and you see how much benefit you are getting, and you can select your target benefit by changing the your parameter, and parameter is basically like either tank size, roof size, um, like this. This picture is for the cumulative town water use. I told you that even you have got the rainwater tank, in some days your tank has got no water because you don't get rain every day. Your tank is not full all over the year. So some days of the year your tank is probably empty. So in those days, your intended use for garden, for toilet flushing, you need to get supply from the normal supply. That's what we call town water use. So in of course in dry year you'll be using more from the this red line. For the dry year you'll be using more from the town water supply to augment your demand. So that software gives you this sort of scenarios. Quite good. I did have many requests to have that software. Now this is about the like our water supply and demand, and to augment our demand. Then the next topic I have got the sustainable urban drainage. Many countries in the world, including Australia, they are trying to implement that sort of sustainable urban drainage. And I have mentioned few items. So they try to implement these measures to improve their drainage system. The earlier practice was to have concrete channel, to have concrete pipe all along concrete pipe, all along concrete channel. And then what they have found now with this efficient drainage system, having concrete pipe, concrete channel, they are shifting burden from one place, from the source, to a downstream place. So then water rushing quickly from every catchment, water rushing quickly to the downstream point, and that downstream point getting sudden flash flood in Australia. In the main cities, some of the main cities, they do get that sort of flash flood, and they don't get enough warning because it's so quickly passing from the catchment to the downstream point that within short notice they get huge amount of flood. So they found that that sort of efficient drainage, the traditional practice, is not really helping our environment. Just all the pollutants transported to the downstream point and it's causing the flood. So now they are trying to come up, first of all, some pollutant treatment, not the plant devices, and then some natural treatment of the pollutants, while at the same time reducing the runoff volume and reducing the runoff amount, so that you can reduce the flood volume, you can reduce the flood amount. Few of these options are shown here. So this is called gross pollutant trap. You don't get to see it's underground. So the inflow coming from one pipe, they create that sort of circulating flow, or they create the vortex automatically without any energy, because you force the water to circulate within that device, and it has to get out from this other pipe. So while you are creating that sort of circulating flow, water creating some vortex at the center. If you rotate the water creating some vortex at the center, while creating that vortex at the center, the heavy particles will come up, and you are forcing the water to get out from other. While after creating that sort of circulation, you are forcing the water to get out from the other pipe, this blue colored one. Then you are collecting. There is a basket here. That basket can be removed. Here I have shown the photo. They have got the truck. The truck come. They remove that sort of. This is another one. Same thing. Similar practice. Your inflow is coming from here. You are creating some circulating flow, and you are forcing the water to go down and then to go up before it can get out. It has to go up, the blue ones, before it can get out. And then because of this, it will dump the solid particles, the bigger particles into this basket, and the truck will come and they will remove the old one and they will put the new one, new basket, and they'll remove the old basket and they will put this new basket. And that truck does this sort of job within 10 minutes. And that trucks you can hire and you can call them and they'll come and they'll do it in 10 minutes. Of course, you have to pay. So this is another device called Rockla. This is another device called HumeGuard. This was developed and tested in my university, Swinburne. You force the water to go down before it can get out. So water has to go up before it can get out. So while doing this, you collect the bigger particles, heavier particles at the bottom. These are, again, this picture is showing how they replace the baskets. This is another one called EcoSol. Same concept, same concept. Different companies producing different types of devices. And these devices are underground. From the top, you just see these manholes, these two manholes. From the top, you just see these two manholes. For this one, they can't replace the basket, but what they do, the truck comes and they insert their pipe, the suction pipe, like vacuum pipe, big pipe, like maybe about 300, 400 millimeter dia pipe. They insert the pipe here and they suck it, all the garbage, dumped here. They suck it, and that suction they takes only about 15 minutes. It's very efficient. I found they take about 15 minutes to clean this whole basket. This basket you cannot move. The other ones, you can move the whole basket. But this one, like this one also, you can't move the basket. You have to use that suction, and they do have that suction pipe. And again, you call them, they come, and they do it within 15 minutes. So these are the manholes for the maintenance and for cleaning. Now, this is another one. They call it bioretention. Especially what they do from the roadside, from the road drainage, all the drainage water coming here. This is stormwater drainage. Keep in mind, not the way, not the your toilet and shower. This is stormwater drainage, and coming to this natural strip. And that natural strip is basically your filter layer. If you take a closer look, it has got the filter material. You see, even it trapped the McDonald cup. People thrown the McDonald cup and then is trapping that McDonald cup here. Anyway, if you take the cross section, so this looks like this. And underneath this natural filtration, eventually it goes downstream. And after some time, after some length, distance, then it will be connected to the normal drainage system. This is called bioretention, widely used in Australia nowadays. This is the plan view of the bioretention system. It has got these plants, and these plants also does some sort of treatment in terms of pollutant suction of trapping some sediments, and sediments, some pollutants trapped with the sediment. So if you can trap the sediment, you are also trapping some pollutants. That's what we have found. You are trapping sediment, but not only sediment, some pollutants also you can trap by providing that sort of bioretention system. That's why we call it bio. The plant is there, and these plants does some biological activities and trapping some of the nutrients. So this is the cross section here. I have got bit better cross section here. Water will be ponding here and slowly will passing through these filter media. Eventually they go to some sort of perforated pipe. It's not normal pipe, it's not solid pipe, it's perforated pipe. So water will get into that pipe and eventually discharge into the main drainage system. So this is called bioretention. There is, you see, the roadside parking. At the end of the parking slope is this bottom one. Parking slope is done in a way that all the runoff from this parking area will go to this area, but underneath they have got this bioretention. This is the whole thing is the bioretention system. You don't understand. If you don't know, you will see some just some grasses, but it's not just some grass. It's bioretention system. Same thing here in a parking lot. They are putting this sort of slot here, gap here. Why this gap? So that this runoff from this parking area get into this thing. So that runoff from that parking area get into this thing, and that whole thing is not some grass and thing. This is the bioretention system. Underneath, it has got that filter layers, and it does the filtration before the water gets into the main drainage system. And lots of work have been done in Australia with this bioretention system. Now, another one is this vegetated soil or grass soil. And this is the old system. They have got the new one is more, uh, you see this, you see this slope here, mild slope. So then we got the automatic, the riding machine, sorry, grass cutting machine. They call it ride on mower. You can cross your grasses while you are riding it, like a small bike. You ride it and it is cutting the grass. So if the shape is like this, then very difficult to ride those like a motor mower. So if this sort of shape, you can ride those mower because you have to maintain these grasses. So you see the water is flowing to a downstream, and when it comes downstream, it collects into that pit collection point into the main drainage system. But before it goes to this collection point, it gets treated with this sort of natural grass. It gets treated with this sort of natural grass, and there is design criteria how much you can treat by this way. There is software. There is software. The software will tell you for certain size of the grass soil how much you can really treat. Mm, Another one is porous pavement. There is no plants, but still by providing that sort of porous pavement, you are allowing penetration, infiltration of your runoff in the ground, and in the ground you use some filter layer like this one. In the ground, you use some filter layer to treat those that runoff on this is car park, and this is from this big car park again. You can do that sort of porous pavement. I did few works using that porous pavement, how much it can clean your runoff. Then there is yet another measure is called infiltration measure. What is infiltration measure? Surrounding there are big buildings, multi-story buildings. From all those buildings, the roof runoff, they divert into this infiltration. So here, this is the filter media here, first with some pebbles and rocks, and if you go down, it will be sand layer. So it does filtration before it connects with the main drainage system. Again, there is software, and that software you can design your filtration size, your filter media property, your how much size you need to achieve particular treatment. So there is a software, widely used software, developed in Australia. So they use that software to calculate, and nowadays government also putting some criteria to the big developments that they have to come up with some sort of treatment by providing any of these sort of things. You can't really go ahead with your big building or big development without providing this sort of treatment facility. Uh, and another one is the constructed wetland. If you go to village area, I'm sure in your India, you can find some of these already exist in the village area. But in the modern city, now they are saying, no, we have destroyed our ecology. We have destroyed our damaged our environment. So we have to provide that sort of wetland to allow natural treatment of our stormwater before it can be discharged to the nearby river or ocean. You have to treat it. So they allow into first initial chamber. So in the initial chamber, some sedimentation will happen, some bigger particle will be settled. Then they come into the main pond or main wetland. In the wetland, they will have lots of these sort of plants. I have more pictures. Yes, this is the initial sediment basin where they trap the sediments. And when they go to the main wetland, there will be some plants like this, and these plants will have some biological activities. They will consume some of the nutrients, pollutants from the water. So while it does help for the flooding as well, because it will retard the flood, it will retain the flood for some time before it overflows, and at the same time it will does these plants will do some biological action, will consume some of the nutrients, some of the pollutants. So it has got the double benefit. But 30 years back they did not consider this sort of constructed wetland. Now again, as I said, even in the city areas, if you want to build, like in Australia, lots of developments, new developments, house development happening. So any new house development happening, suppose you are building 50 houses in one area, the government will impose, okay, you have to provide that minimum size of wetland, and you have to show providing that wetland how much you are benefiting for the flood, how much you are benefiting for the water quality. Mm, so basically, I want to stop here. I wanted to have some more slides, but I did not. I don't want to go more. I think I want to finish here. I want to give you some time to ask me questions. And to me, here it is quarter to one. Quarter to one. I am. I have to sleep. So I think I better transfer the floor to you to ask some question if you have got some question.
Thank you very much, sir, for your wonderful session. So participants will ask questions in chat box, sir, so that you can check out the chat box and clarify their doubts. So participants, you can ask your questions in chat box. Chat box is open now.
Mm. I can see 263 people join. This is
So
very,
267, sir.
very, very fantastic. I'm really happy. I was initially not willing to come to this late night session because this is our fasting month, Ramadan.
Yeah, yeah.
So very tired and exhausted. But when I saw these big participants, that really, exciting me.
Thank you very much, sir. Participants, you can ask your questions in chat box. Speaker is waiting for your questions.
Thank you, Prashant. Thanks for your comment. Mostly all, thank you. So I really appreciate that you have been listening to this talk. Uh, I'm also really happy. I wish to visit you because I have got a PhD student with IIT Hyderabad. Um, like joint supervision, he will do half of his PhD in IIT Hyderabad and then half in my university. So for that, we do have some joint initiative with IIT Hyderabad. So under that initiative, I may come to Hyderabad and I wish to visit you. Mm,
You're most welcome to Lord's College, sir.
okay, I mean, everyone was giving me thanks, but not really any question. That's fine. I think if you don't have, I tell my students that if you don't ask any question, either you understood everything or you didn't understand anything. It can be either you have understood everything, so you don't have any question, or you didn't understand anything. Anyway, but I hope you people understood everything, and I tried to make it very simple. I did not bring the complicated, complex equations, uh, because no one asking question. Then I can ask question.
Yes, sir, they can have chat box, they can reply in the chat
Yeah.
box.
So is it like once in a year you have this sort of once in a year you have got this sort of event or what? Now is all the people joining online or some people on site?
Yes, sir. Pardon?
Is everyone like I can see now 270 people?
Yeah.
Are all of them online or you are some people on campus?
No, no, they are online only, sir.
Oh, everyone is online. That's
Yeah,
good.
online. Because of the
That's good.
huge participants, we have moved on the audio and video. So that's why
Mm,
we have opened the chat session after the end of the session, so that
mm,
if they have any queries, they can go for that. So
okay,
speaker can clarify. So
mm,
that's why the chat box is open now.
mm.
So participant, please open your camera. Sir, Manzur sir,
Yes.
please kindly if you can remove your screen
Yeah. Okay.
so
I'm.
that the
I'm here.
audio. Yeah,
Yeah. I think I can.
just only screen. Yeah, yeah,
Yes.
fine,
Yes.
sir.
Yes.
Yeah,
Mm.
thank you very much, sir.
Yes. Now I can see many people.
Yeah, sir.
Mm. Very
All
nice. Very happy to see you all.
participants, please open your camera as per the ATAL FDP requirement. Participants are requested to switch on their videos. Requirement for ATAL FDP to take screenshots.
I think someone raised the hand.
If a chat box is open,
Yeah. You can write on the chat box.
yes. Feedback link is available in couple of minutes. You can fill out the feedback form. And every participant should give the feedback form because it's a mandatory for ATAL FDP requirement for 80% attendance.
Okay. I can see some people raised their hands, but you can write in the chat box.
Yeah. See, if 80% attendance is not requirement, not required for you, so you will not get the certificate as per ATAL FDP requirement. So feedback form and your attendance is must and should. Please, you can ask questions. Sir, one question is arise here in chat box.
Yeah, one question I can see
Yeah.
whether this sort of treatment is possible for India and China. Yes, it's possible, but bit more difficult because I know that India, especially your Delhi, Bombay, and the Hyderabad, highly densely populated and building dense buildings, but it's still possible, especially in the new areas. Also in the old areas, some countries they are doing. I have seen in Singapore, they are also like densely populated, but still they are doing. China doing some extent. So it's, I mean, it's not impossible. You can say it's difficult, especially when your buildings are already too many buildings in a dense fashion. But still you can do. Someone wrote that any PhD opportunity, yes, university they do offer time to time, but you need to have very high GPA. You can, my details are provided in the brochure, in the flyer. My details are there. You can contact me separately. Universities, yes, giving some scholarship, not many, but some scholarships. But the basic criteria that you need to have very good GPA.
Thank you very much, sir.
Yes, I am. I am. I am very
And we
happy.
are and we are very honored, sir, for your wonderful session. And thank you very much for. We know that it's a late night over there,
Yeah.
so
Yeah.
thank
So goodbye.
thank you very much, sir. Participants should stay back. The second session will be short within a 5 minutes. So before going to the start the session, I will introduce the speaker. Then the speaker will join. Second session will start now. Before going to the start the session, it's my honor to introduce Dr. Ashok G.Matani, Professor retired from the Mechanical Engineering Department, Government College of Engineering, Jalgaon, has over 33 years of experience spanning academia, research, industry, and administration. He holds a PhD in Mechanical Engineering and an MBA in Marketing. His expertise lies in energy, productivity, industrial engineering, environment, and IoT applications and management. With over 200 journal publications, including 60 plus Coopers and 22 Web of Science, UGC K2 index papers, Dr. Matani's research contributions are widely recognized. He has presented more than 235 papers at national and international conferences, including IITs and NITs and institutes listed in NIRF rankings, earning 12 Best Paper Awards. Dr. Matani's Google Scholar metric reflects his impactful research with 516 citations and H index of 15 and I index 22. He has successfully guided three PhD scholars with one more in progress. He has been awarded patents from Australia, Germany, UK, and India, with four more patents accepted for publication. He has delivered 72 keynote addresses, 126 expert lectures, and served as a session chair in 64 conferences, as a reviewer for 17 international conferences and 18 journals, including Scoopus Indexes ones. He actively contributes to research quality. He is also on the editorial board of 20 journals. Dr. Matani has published 30 book chapters and authored 8 books, including 5 international editions. He has coordinated 16 training programs under TEQIP, AICPE, and ISTE sponsorship, and served as an organizing committee member for 12 international conferences. Recognized for his dedication to academic excellence, Dr. Matani's profile score under the National Mission on Education through ICT MHRD GOI is 9.5 by 10. His career is a testament to impactful research, teaching, and continuous knowledge dissemination. So it's my honor, sir, to introduce you. So here you can start the session now.
Thanks for kind introduction. And first of all, I congratulate the coordinator in which I am seeing for the first time since I have given expert lectures in ATAL FDP since last 1 year, and I am seeing the highest number of participants, more than 280 participants. For first time, I'm seeing 280 participants are joining in this FDP. Really, it is worth and means appreciating for coordinators and participants.
Thank you
How
very much,
much?
sir.
Yes, yes. This you got this applause for this, and thanks for this. You deserve this credit. Ki more than 280 participants are joining means it is really appreciating thing. The topic for today discussion is now today's topic for discussion is geothermal and hydropower in civil infrastructure. Actually, we find that majority of these contents are, I have seen that on sustainable development, renewable energy sources, since it is related to civil engineering. And hence, majority of the topics are civil engineering oriented. And here this topic, that is geothermal and hydropower. These are the renewable energy sources that can be integrated into building designs to provide heating, cooling, and electricity generation. By utilizing the Earth's heat, means geothermal or flowing water, that is hydropower, through systems like geothermal heat pumps or hydroelectric dams, significantly reducing reliance on fossil fuels and contributing to sustainable development. Now, this geothermal energy from deep underground is used to generate electricity. This near constant temperature of the earth near the earth's surface is used in geothermal heat pumps for heating and cooling the buildings. This hydropower is electricity produced from flowing water. Now, these key points about geothermal energy, its function, that is taps into the earth's internal heat to produce electricity or directly heat buildings through geothermal heat pumps, which extract heat from the ground even in cold climates, because we have seen that in soil temperature or below soil or below land, we are having the soil is comparatively warm, means heat is there even in cold climates or cold conditions. We have seen that in our, when we are taking water, this water from underground is comparatively hot in cold condition also. These applications are ideal for heating and cooling buildings, particularly in regions with high geothermal gradients. These some considerations are there, or means requirements are there. It requires access to suitable geological formations, drilling deep wells to reach hot rock or water, and can have potential environmental concerns depending on extraction methods. This hydropower, it generates electricity by harnessing the kinetic energy or flowing water through dams or other structures that divert water flow. These applications are suitable for large-scale power generation, flood control, and irrigation systems where integrated with water management infrastructure. In these requirements or considerations are can have significant environmental impacts like habitat disruption, Displacement of communities requires suitable water sources and topography. This is one of the drawback of that. Some habitat or some the residents lying along these dams or along the rivers, they might get displacement. This is one of the drawback of this. Then how to integrate geothermal and hydropower in civil infrastructure. In this building design means geothermal heat pumps. This integrates geothermal heat pumps into building HVAC system, means heating and air conditioning systems, to provide heating and cooling by circulating water through underground loops. Passive design, optimize building orientation and insulation to maximize natural heating and cooling potential, reducing energy demands. In site development, hydropower potential, this analyze nearby water bodies to assess feasibility of small-scale hydroelectric generation, like micro hydro systems for individual buildings or communities. And geothermal resource assessment, conduct geological studies to identify potential geothermal energy sources before construction. These are the main benefits of using these renewable energy sources, geothermal and hydropower. That is, both are considered clean energy source with minimum greenhouse emissions, almost negligible. Reliable power generation, geothermal energy provide consistent power output due to the stable underground temperature, while hydropower can be rapidly adjusted based on water flow. Suppose in monsoon, water is in excess amount of water is available at the time. Probably we have to slow down these we have to reduce the power generation or minimize the power generation, or we have to shut down some hydropower turbines in monsoon when excess water is there. Then energy efficiency can significantly reduce reliance on fossil fuels for heating and cooling needs. Then sustainable development, it contributes to environmentally friendly infrastructure design and operation. This geothermal energy is the process of using heat from Earth's interior to generate electricity. The principle is based on idea that Earth's core is very hot and the crust acts as an insulator to trap the heat. How it works, hot water is pumped from deep underground reservoirs through wells. The hot water is converted to steam. Steam rotates a turbine. The turbine spins a generator that produces electricity. These benefits are, it is renewable, stable, and environmental friendly. Other uses are heating and cooling. Means both we can use in heating as well as cooling the buildings. And district heating and cooling. This geothermal energy can be used to heat and cool groups of buildings, campuses, and communities. This main application of geothermal energy. This geothermal energy can heat, cool, and generate electricity. This geothermal energy can be used in different ways depending on the resource and technologies used. Heating and cooling buildings through geothermal heat pumps, generating electricity through geothermal power plants, and heating structures through direct use. This geothermal energy derived from the heat of the earth can be harnessed both as a source of renewable electricity as well as for heating and cooling. Even the Department of Energy of US government funds geothermal research and development to help stimulate the growth of this geothermal industry and encourage quick adoption of geothermal technology sought by the public and private sectors. Currently, the US leads the world for installed geothermal capacity with more than 3.7 gigawatt power. That is very massive power generation, highest power. With continued R&D success and strong industry adoption, geothermal could meet more than 10% of US electricity demand. Imagine, this geothermal power is fulfilling the energy requirements up to 10%. And highest number of energy means consumed is in the world is in US. So luxurious life is there. And this 10% can be fulfilled through geothermal alone. Means it is having so much potential. Here are some of the interesting facts about geothermal energy. It is base load energy. It is always on. Means base load means it is full-fledged, reliable, totally reliable base load plant. These geothermal power plants produce electricity consistently running 24 hours by day and 7 days a week. Means 24/7 it is working. The power output of the geothermal plant is highly predictable and stable, thus facilitating energy planning with remarkable accuracy. These are excellent means of meeting baseload energy demands or minimum level of demand on electric grid during 24-hour period. This geothermal energy can heat, cool, and generate the electricity. This can be used in different ways depending upon the resource and technology chosen. Heating and cooling the buildings through geothermal heat pumps, generating electricity through geothermal power plants, and heating structures through direct use applications. Even over 100 years of geothermally sourced energy means this can work up to 100 years. It is so long life, hydropower and the geothermal. The first ever geothermal plant was set up in Jalgaon, Italy in 1904. Imagine, means nearly 21 years back, 121 years back. Steam from geothermal source was used to turn small turbine which powered 5 light bulbs. Of course, this was the prototype at that time. Since at the time energy requirement was also very less, very meager. Today, the US leads the world in geothermal power generation, providing more than 3.7 gigawatt of the national grid. This modern geothermal district heating plant was developed in 1892, even before that, in Boise, Idaho. This DOE support direct use efforts is trying to heat more heats and reduce more energy bills. This largest geothermal plant in the world is located in California. This is name of that Geysers Geothermal Complex located north of San Francisco, California. It comprises of 18 power plants and is the largest geothermal installation in the world. Department of Energy is funding at Calpine Corporation's schedule range at the Geysers is first ever abandoned steam field, validating universally applicable technologies. Then geothermal can be closer than you think. Research funded by Geothermal Technology Office seeks way to tap into geothermal sources across the nation. These different types of geothermal plants are there, in which 3 main types are there: dry steam, flash steam, and binary cycle. The type of conversion is part of power plant design and generally depends on the state of the subsurface fluid, that is steam or water, and its temperature. These are the different parts of geothermal power plant. That is steam turbine, generator, condenser, cooling tower, gas removal system, and hydrogen sulfide abatement system. This thermal energy in the form of pressurized steam flows through the wells, through pipelines, and to the power plant. This is at world's largest geothermal plant in Geysers. And which place is famous for geothermal energy? Kenya, Iceland, Italy, New Zealand, Mexico, and Philippines. These are the countries having maximum number of geothermal power plants. In Iceland, the geothermal water temperature ranges from 200 degrees centigrade to 350 degrees centigrade. These geothermal sources are found in form of hot springs and fumaroles. Then, how many geothermal plants are in India? Actually, the Government of India, through its report Geothermal Atlas of India 2022, Geographical Survey of India GSI, has identified 10 gigawatt of geothermal power capacity in 350 identified locations in different regions. The prominent are Tatapani Surajkund belt covers Chhattisgarh and Jharkhand Kambe in Gujarat with reservoir temperatures about 175 plus minus 25 degrees centigrade. India's first geothermal plant is being built in the Puga Valley of Ladakh. The project is being developed by ONGC. This project will use geothermal wells to transport hot water and steam to the surface. This steam and hot water will be used to drive the turbine that generates electricity. The project will include drilling 1,000-meter deep wells. These different phases are there. This first phase will generate 1 megawatt of power. The second phase will explore the potential of geothermal reserve, and third phase will develop the commercial scale power plant. These are some slight challenges are there. This release concerned the project could pollute water resources, destroy habitat, and trigger the earthquake. This is one of the limitations. Are some probable challenges. Even earthquakes can be because of this. Then there are 7 geothermal provinces in India. First one is in Himalayan. It includes Puga and G.Matani region in Ladakh, Sahara Valley, geothermal province in India, then Kembe Basin, then San Narmada Topi Linament Belt, then West Coast, then Godavari Basin, Mahanadi Basin. And notable geothermal areas in India are Manikaran geothermal fields. It is located in Parbati Valley. This is also known for its Manikaran quartz line. And Anhoni Samoni area. This is located in districts of Chhindwara and Hoshangabad. Chhindwara in Hoshangabad in MP. And this is having hot springs ranging from 30 degrees to 42 degrees centigrade. This is the world's most largest geothermal project currently with 750 megawatt of capacity is located in San Francisco. Other projects are developed in many regions, including Western US, Caribbean, El Salvador, Mexico, the Caribbean, Costa Rica, Australia, Japan, Indonesia, New Zealand. So these are different potential sites or think geoenergy top 10 geothermal countries. In this, we are finding the major contribution is of US. In green, we are finding this is that is 3714 megawatts. Indonesia is 2133, Philippines 1918, Turkey 1688, New Zealand, Mexico, Italy, Kenya, and remaining that is Iceland, Japan, and others. And total it is 15,608 megawatts. These are means 1 gigawatt country club. It is known as 1 gigawatt country club. These countries' names. This is breakdown of geothermal in production. Yes, my voice is coming now. Audio and video both are. Voice
Yes,
is clear.
yeah, it's audible.
Okay, sir. Okay, thank you. Now this is breakdown of geothermal energy production, in which we are finding here maximum, that is it is now percentage in pie chart. We are finding this United States, it is having 28.70%. Then Philippines 21.60, then Mexico 10.67, Indonesia 8.92, Italy 8.85%, Japan 5.99, New Zealand 4.87, Ireland 2.26, Costa Rica 1.82, El Salvador 1.69, Kenya 1.44, and different other throughout world only 3.17%. I mean, imagine how this US and Philippines, they are nearly contributing 50%. Half of this circle or this pie chart is contributed, or these geothermal plants are located in US and Philippines. So these are different geothermal and biomass power generation, different countries. Now these 20 largest geothermal power plants in the world, these are largest geothermal power plants in the world. That first one is the Geysers complex, that is California. It is having capacity 1520 megawatt total. Then Lardello complex, that is in Italy, 770. Making Bana complex, Philippines, 460. Heli CD power plant, Iceland, 300. Daraja geothermal plant, Indonesia, 260. Wayang Windu, Germany, this Indonesia, 225. Pelin Pinon thermal power, Philippines, 220. Then Regents power station, Iceland, 200. Then means in Iceland we are having means 4 to 5 power plants, and US is another. It is at another side. It is having. I notice even Kenya is having 130, and France is having 120 power plants. These are 22 world's largest. Means more than 100 capacity, 100 megawatt capacity. These are this identified. Then these are environmental benefits, of course, reduction in greenhouse gases, minimal water use, lower risk of spills. Operational benefits are reliable baseload power, means it is ensured, confirmed, it will be working. Then efficient land use, then scalability. These can be built in various sizes, catering to needs of small communities or large cities. These are these world's largest. Some pictures I am showing you are some details. Which are the world's largest geothermal plants which are at present working. That is Cerro Prieto geothermal plant in Mexico. This Cerro Prieto geothermal plant located in Baja, California, Mexico. The Cerro Prieto geothermal plant has installed capacity of 820 megawatts. It is operating since 1973 and generates about 4% of Mexico's electricity. This Geyser's geothermal power plant, it is generates around 5% of California's electricity, and throughout the US it will be fulfilling 10% of entire USA. So this is 1.17 megawatt capacity. This is the picture of that Geyser's power plant, geothermal plant. These are Geyser's geothermal power plant. Then later in Italy, it is having installed capacity of 769 megawatt and is operational since 1913. Imagine 112 years since it is still working today. It is because I have told you, okay, these plants are having life of more than 100 years. This is Ledero's geothermal power plant, Italy. The Nesjavir geothermal power plant, it is in Iceland, third largest power plant with installed capacity of 120. It is country's capital, that is Reykjavik, and supplies around 2% of the country's electricity. This is these pictures of this. Then Nagamariki geothermal plant in New Zealand. This is having 82 megawatt capacity. So this is the pictures. These pictures which are available on internet, I have taken that, and some websites of these power plants or country's power plants. Then Oahu geothermal power plant in New Zealand, it is having 84 capacity. Then here only 32 countries in the world have geothermal power plants in operation with combined capacity of 16,318 megawatt installed in 198 geothermal fields with 673 individual power units. This is the latest figure. 198 geothermal fields with 673 individual power units. Means in 198 fields or areas, these 673 power units are working in 32 countries out of 198 countries. These are 10 leading geothermal countries. We have seen that. This is the statics of last year, 2023. USA is 3900 megawatt, Indonesia 2418, Philippines, Turkey, Japan also. So this is geothermal map of India. It is officially declared by Press Information Bureau, which is under Government of India, and they are officially releasing these statics. So this I have taken from that PIB website, Press Information Bureau of India, Government of India. So this in red we are finding these are these potential sites of geothermal power plants. And about Puga Valley, it is in Changthang Valley in southern part of Ladakh, about 22 kilometers from Salt Lake Valley. So it is first geothermal project and also world's highest at 14,000 feet height. ONGC has started drilling its first well power project, and it is having high pressure steam at 100 degrees centigrade with discharge rate of 100 tons geothermal energy per hour, considered as a good sign for the project. There are different states of geothermal energy in India at national level. We are having this GSI has identified 340 geothermal hot springs in the country. Most of them are in low surface temperature range from 370 degrees centigrade to 900 degrees centigrade, which is suitable for direct heat applications. This potential for these sites is about 10,000 megawatts. These hot springs in the country are grouped into 7 geothermal provinces, that is Himalayan, Sahara Valley, Kembec Basin, Sen Narmada, Tapi Lineman Belt, West Coast, Godavari Basin, and Mahanadi. These some of the prominent places where power can be established, power plant can be established based on thermal energy are Manikaran in Himachal Pradesh, Jalgaon in Maharashtra, Tapovan in Uttarakhand, Bakreshwar in West Bengal, and Tuwa in Gujarat. These are 5 potential sites. So this is where we are using this geothermal energy for residential heat pump. And the latest, which yesterday I have seen when I was exploring internet, and the latest figure, the latest news yesterday at 11 night I was exploring and this news came on this Leh airport to be the India's first geothermal solar powered airport. That is, it is official declared by Government of India. It is in news. This news is of March 10th. This Leh Kushok Bakula Rinpoche Airport new terminal being developed at an estimated cost of rupees 650 crores is said to become the country's first airport to operate using both geothermal energy and solar photovoltaic power. This terminal is scheduled for inauguration in October this year. Means by October this will be working functional. This work is going on. It will be totally working on geothermal energy and solar PV cells. By using this geothermal and solar energy, this airport will significantly reduce carbon emissions. For the first time, we are introducing this geothermal project at Leh Airport. Instead of conventional air conditioning plant, heat extracted from ground will be used for underfloor heating. Because of this scheme, there will be no carbon emissions and no water uses. Heat energy will be multiplied through heat pumps for heating, cooling, and water circulation. Total of 457 bore wells, each 350 feet deep, are being drilled to harness geothermal energy for terminals operations. This Leh airport is one of the highest airports in the world, situated at an altitude of 3256 meters above sea level. In addition to geothermal energy, solar power will also play a major role in terminals operations. These solar panels with capacity of 500 kV have been installed on rooftop of the terminal building. Additional 200 kV of solar capacity is planned in the car park, bringing the total solar power generation up to 700 kilowatts. This airport's total power consumption is estimated to be 2.5 megavolt amperes, but due to geothermal energy, 2800 kW will be saved. This terminal building will also use advanced infrastructure for energy efficiency. No artificial lighting will be required during the daytime thanks to special glass panels. Unlike most airports which use double glazed glass, installing triple glazed glass unit 56 mm thick to prevent heat transfer. These precautions are especially made here in this airport, Leh Airport. Using a special glass on the rooftop to allow natural light. Once completed, the new terminal will have the capacity to handle 1,000 arriving and 1,000 departing passengers daily. Besides its thermal efficiency, the terminal building is also coming up with many local architectural touches and artworks which they say are being created by local artists. These flight operations at India's highest commercial airport in Leh are affected. Of course, this is also one of the reasons because of too hot temperature, just like it will be now in May in majority of the parts in central India. Also, we are facing this 46-47 degrees centigrade in May. Particularly 15 to 30th May, majority of central India province or parts of states of central India, they are facing these heat waves. This Leh has affected the daytime temperature soared to 46 degrees, making air too thin for safe aircraft operation. This extreme heat is impacting air travel, causing delay and disruption at the airports. And it is also one of the factors affecting this. And this world's first solar power airport in India, we are having Cochin. It is world's first solar powered airports. It is working now. And now, as per Honorable Minister, this more than 90 airports in India will be carbon neutral by means of course they have projected means the works on these airports is going on. Of course, this is the news 4 months back. And here we are finding Cochin International Airport, which is totally working on solar power. These even airports located at Delhi, Bangalore, and Kochi have already set the course of environment friendliness for others to follow. Indira Gandhi International Airport in New Delhi is on path to zero emissions or carbon neutrality. In this airport's power is derived from solar and hydropower energy, creating sustainable development choice. This airport was first in the country to ban single-use plastics and later became the first airport ever to clock 1,000 taxi boat movements. This Cochin International Airport in Kochi is carbon neutral since 2015, means it is working since last 10 years. Even Kempegowda International Airport in Bangalore is also achieved the coveted energy neutral status by 2021. This airport operator Bangalore International Limited, RYL, has successfully saved 22 lakh units of energy in financial year 2021. It was then further implemented chiller plant optimization in heat, ventilation, and air conditioning. They are building Kushok Bakula Rampur Airport in Leh Ladakh to become the nation's first carbon neutral airport. It taking a step to encourage sustainability in the Ladakh region. This use of geothermal energy via solar plant will create a sustainable light for ambitious Ladakhi people. This civil aviation is highly visible sector. It is very high profile sector that attracts a lot of attention. To this contribution to this greenhouse gases and carbon emissions, it adds just 2% of world's carbon emissions. Now, before starting this hydropower, I will show you one video in which we can see.
Yes, sir. Yeah, it's open.
For the next few years, they plan to focus on shallower superhot geothermal zones up to 5 kilometres deep. This approach allows them to refine the technology's economics and build expertise before tackling deeper, ultra-high temperature drilling in the future. Challenges definitely remain for Quays, including rock debris removal, maintaining well stability at extreme depths, and securing a reliable supply chain for the gyrotrones, which haven't yet been optimised for drilling conditions. While the potential is enormous, scaling up from test drilling to full-depth commercial wells will be a significant leap. And as far as I'm aware, Quays haven't got a solution to the need for flexibility in any generation technology that is going to integrate into a grid with lots of variable renewables. Let's move on then to the next couple of technologies who are a bit further ahead with their real-world trials, and they have flexibility built into the tech. Next up is Enhanced Geothermal Systems, or EGS. Unlike conventional geothermal, which relies on naturally permeable rock to circulate fluid and extract heat, EGS create their own permeability by injecting high-pressure water to fracture deep rock formations. If that sounds a lot like how fracking works, that's because it is. More on that later. Fracking allows EGS to tap into heat in areas without natural hydrothermal conditions, greatly expanding geothermal's potential reach. The Forge project in Utah, led by the US Department of Energy, is a key research center for EGS and has already made progress with successful test wells, refining methods for managing water flow and heat transfer to optimize power generation. Pioneering EGS startup Fervo Energy recently completed a pilot in Nevada where they adapted oil and gas technology to drill horizontal well pairs, demonstrating a reliable flow of heat. And there's another benefit to these artificial reservoirs. They allow energy to be stored. This isn't possible with natural geothermal reservoirs because the rock is permeable. That means they can't hold water in place, so any extra water added just dissipates. But EGS reservoirs are surrounded by impermeable rock and should be able to store fluid under pressure. Fervo plans to take advantage of this by controlling the rate of fluid injection and extraction. They say that they can charge and discharge heat as needed, enabling the system to act like a massive underground battery. While promising, EGS faces environmental and social risks similar to those in oil and gas fracking, such as groundwater contamination. However, EGS typically operates at greater depths and often uses pure water rather than chemicals, and it doesn't involve hydrocarbons, so there's no risk of petroleum-based pollutants contaminating groundwater. Another common concern with fracking is that it can cause earthquakes. Injecting fluids deep underground, whether for oil, gas, or EGS, can lead to significant seismic activity. It's not just theoretical, it has happened several times. The 2017 Pohang earthquake in South Korea, for example, reached a magnitude of 5.5 and caused extensive damage. Investigations found that EGS fluid injections likely triggered this earthquake. To mitigate these risks, EGS operators, like Fervo, carefully select sites away from major fault lines and monitor seismic activity in real time. If seismicity increases, they adjust or halt injection rates to stabilize subsurface pressures. Another downside is that while EGS solves some key issues with traditional geothermal, some challenges remain. Since it circulates water in direct contact with hot rock, it can dissolve minerals and salts, creating highly mineral-rich water that can lead to scaling and corrosion in pipes and equipment. This means higher maintenance costs and the need for corrosion-resistant materials or water treatment systems to prevent buildup. That particular challenge is avoided by the final next-generation geothermal technology that we're going to look at, closed-loop geothermal. Unlike conventional and enhanced geothermal systems, which need fractures in the rock to circulate water, closed-loop systems circulate fluid within a sealed pipe loop underground. This setup lets the fluid absorb heat from the surrounding rock without direct contact. getting rid of risks like groundwater contamination, scaling, and corrosion. By containing the fluid within the system, closed-loop geothermal doesn't need natural permeability for fracking. EVA is the leader in this field. They've already completed a demonstration project in Alberta and are now developing their first commercial site in Germany, where they've already drilled to a depth of 7 kilometres. This site is expected to start delivering its first power to the grid as soon as mid-2025, and the full capacity will be reached over the year or two after that. Unlike AGS, which get a lot of surface area of hot rock in contact with water due to the many tiny fractures, closed-loop systems rely entirely on the surface of the drilled boreholes to transfer heat. To get enough heat transfer in the fluid, the wells need to reach deeper into hotter rock formations and have long, often branching sections to increase total surface area, with tens or even hundreds of kilometres of horizontal piping. Closed-loop systems also offer flexibility, as the circulation of fluid can be slowed or stopped to store heat in the loop when demand is low, allowing it to release more energy during peak demand times. However, this tech comes with its own challenges. Closed-loop systems require much more underground infrastructure than other geothermal types. There is simply a lot of material in all those kilometres of pipe. Furthermore, horizontal drilling, particularly very deep underground, is both technically challenging and costly. While EGS involves some horizontal drilling, closed-loop designs depend on it far more to maximise heat transfer from the surrounding rock. These new technologies could make geothermal power viable far beyond volcanic regions, potentially opening up sites worldwide instead of just geothermal hotspots. That will only happen if it is cost competitive with alternatives, and today it is not. Geothermal has only come down in price a little in the past couple of decades, nothing close to the sharp decreases we've seen in other clean energy technologies like solar and lithium-ion batteries. But that's traditional geothermal. And there are aspects of next generation geothermal that make me think that we might see rapid improvements there. I expect next generation geothermal to see faster cost reductions than traditional geothermal, thanks to key advancements that tackle long-standing challenges. Traditional geothermal projects have faced high exploration risks, much like oil and gas drilling. Not every well yields a viable resource, as success depends on finding Goldilocks conditions with just the right permeability and heat. In contrast, new geothermal technologies from companies like Quaise, Vervo, and EVA create these conditions artificially, removing the need for perfect geological settings. Recent progress in drilling technology is also driving down costs. The oil and gas industry has shown how rapidly drilling costs can drop with experience and scale. In North American shale gas, drilling times for horizontal wells fell from 3 months to just 8 days, transforming the economics. Those advances obviously resulted in a whole lot more fossil fuels becoming economic to extract, which has not been great for the climate. But on a more positive note, we're seeing similar improvements in geothermal too. Drilling speeds at the US Department of Energy's EGS demonstration site Forge improved over 500% in 3 years, while well development costs fell from $13 million to under $5 million per well between the first 2 large-scale commercial EGS pilots. Finally, closed-loop systems, like those developed by EVA, also benefit from modularity, producing multiple similar components with cost savings as experience grows. With these factors combined, it's likely that next-gen geothermal will see faster and more significant running through the night. It doesn't take up a lot of space in the car, and with the flexibility to recharge with solar in just a few hours, I can stay off-grid without worrying about power. And for home backup, especially during summer storms or bushfire season, EcoFlow's DP3 model is a great option. It's designed for longer duration use, keeping you covered when you need reliable.
Yes, it is.
Ambitious project is underway. Picture wells plunging miles into the earth, deeper than twice the height of the world's tallest skyscraper. This isn't a search for oil, but something far more revolutionary. Google and a startup called Vervo Energy are building a power plant fueled by the Earth's fiery core. They're using advanced drilling techniques similar to those used in the oil and gas industry to create artificial hot springs deep underground. The potential is staggering. Geothermal energy could provide reliable 24/7 power on a massive scale. But why is one of the world's largest and greenest tech giants embarking on such a controversial journey in the construction industry? Throughout history, harnessing this geothermal power has tantalized scientists and engineers. The journey began in earnest in Italy's Tuscany region. Prince Piero Ginori Conti in 1904 created the world's first geothermal generator, successfully powering 4 light bulbs and providing the concept. Larderello, Italy, soon after became the birthplace of the first commercial geothermal power station. The idea behind geothermal energy is undeniably elegant. See, deep underground, the Earth's heat turns water into steam. Geothermal plants capture this naturally occurring steam, essentially free fuel, and use it to drive turbines, generating electricity. It's like a coal-fired power plant, but we're tapping into the planet's natural heat instead of burning coal. And here's where the numbers get exciting. The Earth's interior contains an estimated 1 times 10 to the power 19 terajoules of heat energy. While much of it is too diffuse to harness, even a small fraction could power the world many times over. As of 2019, geothermal energy provided 15.4 gigawatts of electricity globally, a small contribution, but with immense growth potential. But what about places without those easily accessible steam reservoirs? This is where innovation kicks into high gear. Engineers develop enhanced geothermal systems, EGS. These systems involve drilling multiple wells and injecting water into hot, dry rock under high pressure. The water fractures the rock, creating pathways so it can absorb more heat from the surrounding rock. This heated water is pumped back up, generating steam for electricity. The potential of geothermal energy is staggering. It's a reliable, always-on source capable of providing that rock-steady foundation for future energy grids. It offers a pathway to a cleaner, more sustainable world, and Google is demonstrating that it's not just a dream, but an achievable goal. For Google, sustainability isn't a buzzword. It's been a core value from the very beginning. Since achieving carbon neutrality back in 2007, the company has led the charge towards a clean energy future. In 2017, they reached an astonishing milestone. Google became the world's largest corporate renewable energy buyer, matching their electricity consumption with clean power sources. But they didn't stop there. Their announced purchase of 1,600 megawatts of renewable energy is historic. This landmark deal expands their clean energy portfolio by over 40%, bringing their total capacity to 5,500 megawatts, enough to power 1 million homes. Picture solar farms spring up across the Carolinas and Texas wind turbines dotting the European landscape, all fueled by Google's commitment. These aren't just abstract numbers. Google's investments amount to over $7 billion in new renewable energy infrastructure and countless jobs in communities across the globe. But what truly sets Google apart is its focus on additionality. This means they're not just buying power from existing wind and solar farms, but directly stimulating the creation of new projects. Think of it like this. Each Google-funded solar panel and each new wind turbine directly increases the total amount of clean energy flowing into power grids worldwide. Google's commitments to driving change is turning up the heat, and not just in the Earth's core. In May of 2021, they made headlines by signing the world's first corporate agreement for next-generation geothermal power. Partnering with the clean energy startup Fervo, they're developing a revolutionary project designed to inject carbon-free energy directly into Nevada's grid, powering their data centers and the Las Vegas cloud region. Unlike traditional geothermal plants that rely on tapping into naturally occurring hot springs, Fervo takes a proactive approach. They employ advanced drilling techniques from the oil and gas industry to reach deep into the Earth's crust and maximize their contact with superheated rock. These horizontal drilling techniques allow them to extend their wells far beneath the surface, dramatically increasing the potential for heat extraction. Fervo's approach is meticulously planned. They use sophisticated geological modeling to pinpoint the ideal locations for their wells, ensuring they hit the zones with the highest temperatures. This maximizes the potential for power generation. Fervo deploys an extensive network of fiber optic sensors throughout their wells to optimize their operations further. These sensors act like a continuous monitoring system, providing real-time data on the geothermal system's temperature, pressure, and water flow. This wealth of information is fed into powerful analytics software, allowing Fervo's engineers to make data-driven decisions to optimize energy output, detect potential issues early on, and constantly improve the system's overall efficiency. This combination of advanced drilling, real-time sensor data, and cutting-edge analytics is what sets Fervo apart. They are transforming the way we think about geothermal energy, demonstrating that with the right technology and engineering, it can be a far more versatile and widespread clean energy solution. Google's not just buying energy from this project, they're fueling innovation. Their collaboration with Fervo includes developing AI and machine learning solutions to optimize geothermal power generation. Think of these systems as the brains of the operation, analyzing real-time data on temperatures and energy output, pinpointing the sweet spots deep underground for maximum power generation. The Fervo project takes this innovation underground, proving that next-generation geothermal can be a smart, flexible, and reliable source of clean energy on a large scale. The Fervo project brings its Nevada operations closer to that 24/7 clean energy goal while demonstrating that cutting-edge geothermal power can replace fossil fuels and transform the global energy landscape for the better. This groundbreaking approach makes it possible to access the Earth's heat almost anywhere, overcoming the geographical limitations of traditional geothermal power plants. Adapting drilling and fracturing techniques perfected by the oil and gas industry, Fervo is unlocking a vast new potential for clean energy generation. Their process resembles constructing a meticulously engineered artificial hot spring. It begins with drilling 2 wells to astonishing depths, over 7,000 feet straight down, exceeding twice the height of the Burj Khalifa, the world's tallest skyscraper. These wells then extend horizontally beneath the Earth's surface, maximizing their content with the surrounding hot rock. Next, Fervo employs hydraulic fracturing, or fracking, to create a complex network of fissures in the rock, essentially connecting the 2 wells for optimal water flow. The magic happens when cold water is injected into one well. As it courses through the fractured, superheated rock, it absorbs massive amounts of heat. By the time it returns to the surface through the second well, the water's temperature can reach a staggering 375 degrees Fahrenheit or higher. Fervo's Nevada pilot, after a month of rigorous testing, proved a resounding success. Temperatures at the bottom of the wells consistently hit a blazing 375 degrees Fahrenheit, 191 Celsius, driving significant water flow capable of generating approximately 3.5 megawatts of electricity. While slightly below initial projections, Fervo CEO Tim Latimer remains confident that further refinements will increase power output. He underscores that this project marks a milestone, outperforming similar efforts in France that rely on lower temperatures and naturally occurring fractures instead of Fervo's engineered network. This breakthrough technology could be a vital solution for tech giants like Google. Their energy-intensive data centers demand a consistent power supply. While wind and solar form the backbone of their green efforts, the variable nature of these sources presents a challenge. Geothermal energy, with its 24/7 reliability, has the potential to fill that crucial gap. If you found this video fascinating, give it a thumbs up. Subscribe to our
I have shown you these slides intentionally videos so that we should have clear picture how this geothermal power plant is and how it is operating and what are different latest development throughout world. Even Google is now establishing or commissioning this new renewable energy source for its day-to-day working. Means when Google is exploring this means that is the end of this, because Google its satellites or sensors give the clear exact picture and potential, how much potential of any particular source is there, and hence they have entered in this. Means no any other cause. One establishment, it is commissioning is there. Not much fuel is totally freely available underground hot water. Now we go to another topic, subtopic, that is hydropower. This in civil infrastructure, this hydropower refers to the generation of electricity using the force of flowing water, typically through system of dams, reservoirs, and canals, which are considered part of civil engineering, allowing for harnessing of water's potential to produce electricity as a renewable energy source. This hydroelectric energy is rendered by converting kinetic energy from water into electrical energy. To harness this power, enormous hydroelectric infrastructures are built to extract maximum power from this renewable emission-free local resource. And how this works, this picture is there. This converting a potential difference of water into electricity by transferring between 2 points at different heights or elevations. This flow of water is forced through hydraulic circuit that connects 2 points at different heights called drafts, in which water gains speed as potential energy is partly transformed into kinetic energy, and this turbine transforms this kinetic energy into mechanical energy, which generates electricity. This flow of water leaves the turbine and is released back into river almost without speed, with potential energy that corresponds to the height of the outlet. Means imagine of this. Please give concentration on this or special attention on this. Overall output from this process is very high, between 90 to 95%, capturing almost all the potential energy of the water. Power loss is due to low pressure in the hydraulic circuit, to the friction in rotation of the hydraulic power unit, and losses in electrical equipment. This another process is also pumped storage hydroelectric power plants, which make power plants reversible. These convert electrical energy into potential energy by pumping water into upstream reservoir or tank. These are different key aspects of hydropower in civil infrastructure, that is dams, intake structures, penstock, turbines, generators, spillways. These are benefits of hydropower in civil infrastructure: renewable energy, flexible power generation, flood control, irrigation support. Slight challenges are there, limitations of these are also there. High initial construction costs, because dams and SOD infrastructure can be expensive. Environmental impacts: large dams can disrupt ecosystem, can displace communities. Also, this is one of the topic. Even in some localities, this it is yet not confirmed, but some rumors are there. Where large capacity power plants are there, hydropower plants are there, slight risk of earthquakes are also there, but it is not yet confirmed. It is just linked with that. And seasonal fluctuations, water availability can vary depending on weather patterns impacting power generation. Then different types of hydropowers are based on design, that is impoundment, diversion, and runoff river power. And then which is most suitable place for construction of hydropower plants? The best place to build a hydropower plant is in hilly area or mountainous area with sufficient amount of falling water. Means where natural circulation is there. Why hilly areas are best? Because water flows. Hilly areas have steep slopes and fast flowing rivers, which create lot of potential energy. Water availability: rivers originate in hilly areas, so there is plenty of water available. Other consideration: discharge and head flow. This potential of hydropower plant depends on availability of discharge and head flow. Then water quality: no any pollution is there. Accessibility: construction site should be easily accessible. The distance to load center: this power should be close to load center to minimize this cost of power transmission. Advantages are: it is renewable energy, affordable, flood control, irrigation, backup water, same water we can reuse it. Clean drinking water is also provided through this. Then economic development is there. Then economic development: hydropower promotes economic development, generation of local employment. Slight disadvantages are there, limitations are there. Cost is somewhat more. Environmental impact is there. Design dams and reservoirs can disrupt river ecosystem. Then can affect fish migration. Then can impact water quality. Can harm aqua, flora, and fauna. This is also one of the topic. And displacement of people, because when dams are made, the catchment area of this river base or water resources going to make large dams. In this, some movement of people or displacement of people can be there. People living in areas where dams are built may need to relocate. That is the topic. Then vulnerable to droughts. Then hydropower production depends on rainfall. During drought, costly work may be required to divert another river to feed the reservoir. This is also one of the challenge. Then limited plant locations. Not every piece of land is suitable to build a dam. Then this is what is the cost of hydropower? That is average power production expenses per kWh. That is in the US, hydropower is produced per average of 0.85 cents per kWh. It is about 50% of cost of nuclear, 40% of cost of fossil fuel, and 25% cost of using natural gas. Means it is that much economical if we consider the economic point of view, power generation from hydropower. Then what is price of hydro project? In of course, this is this 3 years back data. Hydro systems had an average installation cost of $2,881 per kilowatt installed. This is average cost of commissioning of these hydropower plants. Then this cost of 1 megawatt hydropower plant in India can range from 5 to 6 crore rupees, depending on project's location and size. These different factors affecting cost are land and labor, project size, seating and access, geology, and finance. Other considerations, this cost of civil and EM works, plant load factor depends on water availability, and environmental social impact of project also affect the cost. And operation and maintenance. This is nearly 1.5% to 2.5% of investment cost per year, O&M cost. What is the lifespan of hydropower? Imagine this. Means both geothermal and these are having nearly 100 years lifespan. This lifespan and durability, this have long lifespan, especially for 50 to 600 years. Then hydropower is the base conversion efficiency, about 90% efficiency water to wire. It requires little high investment but has long lifespan with low operation and maintenance costs. Because water is easily available, freely available. No any fuel cost is there. India's hydroelectric potential is estimated at 1,48,700 megawatt at 60% load factor. This total hydroelectric power generated in India was 156 terawatts, excluding small hydro, with average capacity of 38.71%. Then Koina is the highest, means biggest or largest hydroelectric plant in India. This dam consists of 4 dams, including largest dam on Koina River, Maharashtra Satara district. The upcoming projects in India in last year, these are at completion of Parbati 2 phase 2 and integration of Dibang multipurpose hydropower projects. This Parbati 2, it is constructed by National Hydropower Corporation, is constructing these 4 units of 800 megawatts. Means that is quite good capacity. 800 megawatts hydroelectric project in Himachal Pradesh, which was actually last year it has been commissioned. And Dibang, it is in Arunachal Pradesh. It is having 2880 megawatts hydropower capacity. Then Subansiri Lower, that is NHPC is constructing 8 units of 2000 megawatts along the Assam and Arunachal Pradesh border. These units are expected to be completed by this March, means by the end of this month, and remaining units by next May. Other initiatives by Government of India, government is fast-track construction of 2 pumped storage projects. Government has issued guidelines to promote the development of pumped storage projects. This government is providing budgetary support for flood moderation and storage hydroelectric projects. This small hydro project, it is the development of hydroelectric project which harness energy from flowing or falling water from rivers. This capacity up to 25 megawatt is called as a small hydro project. In this, how it is working, this is potential energy. Then it is converted to hydro energy and through penstock, and it is where mechanical energy, and after this it is generator powerhouse, and it is to grid, long distance power lines grid. And this water through turbine discharges again sent to river for irrigation and drinking purpose also. This basic principle of hydropower is there, that is P equal to G into Q into H into efficiency, that is P is power in kilowatt, Q is turbine discharge in cubic meter per second or cubex, H is net head in meters, efficiency, N is overall the unit efficiency, that is turbine and generator efficiency, and G is gravitational constant, that is 9.81. These are small hydropower projects up to micro, that is up to 100 kW, mini, that is 101 kW to 2 megawatt, and small hydro 2 megawatt to 25 megawatt. These are classification of small hydropower projects. And even Government of India, this cabinet has approved these measures to promote hydropower sector. The cabinet, chaired by Honorable PM Sir, has approved following measures to promote hydropower sector. That is, large hydropower projects to be declared as renewable energy source. Then tariff rationalization measures, including providing flexibility to developers to determine tariff by backloading or tariff after increasing project of 40 years. It is increasing debt repayment of period to 18 years and introducing escalating tariff of 2%. Even budgetary support for funding flood moderation component is also made, which this is 1.5 crores per megawatt up to 200 megawatt projects and rupees 1.0 crore per megawatt for above 200 megawatt projects. This is electricity production from hydropower. These are different countries. Here we are finding the highest it is coming in Switzerland, Iceland, Norway, and Albania. So this this hydroelectric project is fulfilling the demands of sustainable development goals also. So these are this 1 to 13 here. Actually, total 17 sustainable development goals are there. These have been marked or declared by United Nations. Out of the 17 SDGs, 13 are fulfilled through water or this hydropower. Some of the major hydropower companies in India are NTPC, then Satluj Jal Vidyut Nigam, Tata Power, Dairy Development, Hydro Development Corporation, Jayaprakash Power Ventures, GMR Power, and Urban Infra Limited. This public sector accounts for 92.5% of India's hydroelectric production capacity. This National Hydroelectric Power Corporation, Northeast Electric, all these are public sectors. Globally, 4250 terawatt hours of clean electricity was generated from hydropower, and 1.5 times the entire electricity consumption of European Union, and more than all the renewable generation combined. Means it is so huge potential is there for hydropower. These hydropower startups in India, we are having this. There are 101 hydropower companies, startups, which includes Renew, Greenco Power, Atria Power, NSL Renewables, and NHPC. Out of these, 30 startups are funded with 21 having secured Series A plus funding. Over last 10 years, average of 2 new companies have been launched annually. Even several of these have started been founded by alumni of IIT Delhi, Harvard Business School, and Harvard University. Top 5 hydropower startups in India are there. That is Renew. This is name of that company. It is founded in 2011. It is in Gurugram. It is public limited. Total funding is $2.04 billion. Investors are CPP investors, Goldman Sachs, and 20 others. Then its traction score, it is 64 by 100, and competition rank, it is 7 up to, means total 246 competitors are there. Out of this company is at the 7th merit or leading Renew company. And this is traction score. This is proprietary based on companies standing against other companies. This score is composed of 4 metrics. That's IG score, executive score, growth score, and team score. Then Greenco Group. So this is founded in 2006, working in Hyderabad, and its competitive rank is 3 of 103 competitors in this group. Then Atria Power. This is working in Bangalore since working 1999. Its competitive rank is 13 of 103 competitors. Then NSL Renewable Power. This is established in 195, Hyderabad base. Its competitive rank is 22 of 103 competitors. Then NHPC, of course, it is Government of India. It is in Faridabad. It is public sector. Then this is the official declare means statement declared by a PIB, which I was telling you, Press Information Bureau. So this is declared officially announced on 7th August 2024 at 3:43 p.m. regarding hydro energy projects posted on this date. These are different initiatives by Government of India. Even TV commercials are aired on prominent news and general entertainment channels such as Kanak TV, Colors, Oriya News, 18 Oriya, Kalinga TV, and OTV during prime time. These are encouraging this popularity of this hydropower. They are giving this advertisement in depth. Even pan India execution of Google advertisements, social media campaigns, and digital website promotions. These are hydropower projects with more than 25 megawatt capacity in India. These are, it is a leading total 2831.55 megawatt capacity. This is another 2831. Then pumped storage projects, it is having 5075 megawatts. Then small hydro projects up to 25 megawatt, this is having 56.50 megawatt capacity. These are 3 hydro projects. Then biomass power project, this is 2 megawatt. And even development of solar parks and ultra mega solar power projects is also going on in this. These are incentives provided by central financial assistance for implementation of major renewable energy scheme promotions. These are schemes offered by Government of India. Then these are the list of power plants in India. This is, of course, this is the figure of last 2 years back, 3 years back. But these are these remarkable are major projects working in today. First one is Tehri. It is highest dam in India with collaboration with USSR. It was built in 1978. It is in Uttarakhand on Bhagirathi River. Then Sri Salem, it is at River Krishna in Andhra. Established in 1960, it is second highest, largest hydropower project in Bakra Nangar in Punjab, both Punjab and Haryana, which is in Satluj River. This was established in 1948, means just after independence. Then Nagarjun Sagar Dam, it is also one of the famous dam. World's largest masonry dam is protected by 26 gates, established in 1960s in Krishna River. Then Iduki, it is in Kerala, Periyar River. Then Sardar Sarovar, it is in Gujarat, Narmada River. And Shivan Samudra, it is in Kaveri River and Karnataka. It was established in 1902. First hydropower project in India. Imagine 21 to 3 years back. These are different. Teesta Dam, then Koyna in Maharashtra, 1956, largest hydel power project in India. This then Salal, Ranjit Sagar Dam, Machkund Dam, Hirakud, Odisha. These different. These are total 20. Then top hydropower companies are advocating for renewable energy sources. These are different companies or startups, what we call that. Voith Group, then Enrich Hydro, which was established in 1852. Imagine how much old it is. Based in Austria. This General Electric, of course, is formed in 1892. J.P. Morgan, Thomas Edison, and Charles Coffin founded the company. Then China, 3 Gorges, it was established in 1993 in China. 1. This is the place from where we got this COVID. This case is spread from one city in China. So this company is there. There are 3 projects. Then Alpha Laval, of course, this company is also working in India. Hydro-Quebec, it is in Canada. Then ABB, of course, this is also working in India also. It is Swiss company. Engie, it was in France. Tata Power in India, we are having, it is established in 1919. It is subsidiary of Tata Group. And Siemens Energy, of course, it is of Germany. Then this is the complete list of hydropower plants in India. I am showing you that figures. Of course, these are, it is the latest figure, that is current capacity of hydro plants in India, that is 46,850 megawatt. India global position in terms of installed capacity, fifth at world level. Then there are 197 hydroelectric power plants in India at present today. Most innovative hydropower are latest technology used in that is BC Agro at their energy centers. These are different names of companies. This is on river. This data is there in which name of plant, river, state, year of commission and capacity. This is the figure. Total 38 hydroelectric projects, means 41. Then I will show you one video in which we can have what is the new technology going on in which will be revolutioning this hydropower. New technology
Welcome back,
developments are there.
gentlemen. Today, we're exploring turbulent and
I'm sharing that video where we can have imagination what is going at world level in this hydropower projects. Yes, it is now.
Yeah, sir. It will be ready.
the other at 800. Day or night, rain or shine. Welcome back, gentlemen. Today, we're exploring turbulent and innovative Belgian company shaking up the hydroelectric power scene. Their game-changing turbulent turbine, a marvel of modern design, is more affordable and economical than traditional powerhouses. Just picture it. You could have it humming along in a river or canal with minimal elevation changes in a week's time. Day or night, rain or shine, it's generating electricity for you. Here's how it works. This smart turbine creates a swirling vortex in a concrete basin, turning water flow into spinning energy. Depending on the water's flow rate, it can generate up to a whopping 70 kilowatts. Enough juice to power 6 or 7 households. And the best part, it's environmentally friendly. The design ensures our aquatic friends remain unharmed, and its impressive lifespan extends beyond 100 years. Truly, a step forward in renewable energy. Open Hydro. Continuing our journey into renewable energy, gentlemen, we set sail to Open Hydro, North America's largest tidal power plant off Canada's coast. Imagine a structure towering 5 stories high, weighing 1,000 tons. This isn't just another behemoth. It's a green giant, generating a staggering 16 megawatts of electricity, enough to power a small town. This marvel of engineering is the product of Irish company Open Hydro and Canada's Emera, and it's been harnessing the power of the sea since November 2016. Now, get this. Open Hydro features 2 turbines, each 53 meters in diameter, anchored by cables a solid 120 meters long. This means, from turbulence vortex to Open Hydro's tidal prowess, we can power about 1,000 homes without emitting a trace of greenhouse gas. Landistry. Now, we journey to the Netherlands to meet the next game changer, Landistry. Landistry's screw turbine, true to Dutch expertise in water management, turns canal height differences into electricity. It's a marvel, generating power from just a 1 meter height difference and a water flow of 500 liters per second. Just like its predecessors, the Landistry screw turbine is compact, easy to install, and kind to your wallet with its low maintenance costs. It's resilient, withstanding harsh canal conditions and ice while ensuring the safety of our aquatic friends. Impressively, it can churn out up to 100 kilowatts of electricity continuously and remains a reliable source of energy even during periods of low water flow. Best of all, it's a zero-emission solution. Water odor. Now, we're about to witness another trailblazer, water odor, a groundbreaking technology that harnesses power from slow-moving water bodies. Whether it's streams, rivers, canals, or even underwater ocean currents moving as slow as 3 kilometers per hour, water odor has got it covered, generating anywhere between 1 kilowatt and 1 megawatt of electricity. Compact,
Portable and eco-friendly, it fits perfectly alongside our other zero-emission solutions. You could fit up to 20 units in the back of a truck, bringing power to the most remote corners of the globe without hurting local flora and fauna. Born from the genius minds at the University of British Columbia, Water Rotor is not just a concept, but a proven technology, powering remote communities and providing backup for off-grid location. Another fascinating stop on our renewable energy journey. Tom Sock. Gentlemen, continuing our renewable energy expedition, we've cruised across Belgium, Canada, the Netherlands, and through the innovative waters of Water Rotor. Our journey now brings us to the Show Me State, Missouri, home of Tom Sock, the world's largest pump storage hydroelectric power plant. Picture this. Two reservoirs, one towering at 720 meters and the other at 450. When power demand surges, they release water down to spin turbines, generating electricity. At night, the water's pumped back up, using surplus power from other sources. Simple, yet ingenious. Constructed in the 1960s, Tom Sock, named after the nearby mountain, started with 800 megawatts of power. Today, after an upgrade, it stands mighty at 1,020 megawatts. As with all our stops, Tom Sock is a testament to efficient and sustainable power generation, retaining up to 85% of the energy used to pump water back up. Another eco-friendly giant on our green energy tour. Orders you work to. From Missouri's Tom Sock, our eco-energy odyssey now takes us across the Atlantic to the breathtaking Oxtal Alps in Austria, where the future is being forged. Gentlemen, let me introduce you to Löhninselwerk 2, the largest pumped storage hydroelectric power plant in Austria, currently under construction. Think back to our previous stop. Löhninselwerk 2 functions similarly, harnessing the power of gravity. Now, picture this. Two reservoirs, one perched at a staggering 1,800 meters, the other at 800. Four turbines, a 1,000 megawatt capacity, all tucked neatly inside a mountain. This is a 2.2 billion euros project creating jobs, promoting sustainability, and set to power 1 million homes. Scheduled to be completed in 2037, Löhninselwerk 2 is a testament to Austria's commitment to sustainable future. Another intriguing pit stop on renewable energy. PB3 Powerboy. From Austria's Alps, let's shift our gaze to the vast Pacific Ocean off the California coast. There, the American company, Ocean Power Technologies, is testing its latest innovation, the PB3 Powerboy. Imagine a device that uses the kinetic energy of waves to generate electricity. The PB3 Powerboy is just that. Adaptable to depths from a shallow 20 meters to depths of 3,000 meters, it provides uninterrupted electricity and can store surplus power. But this Powerboy is not just about energy, it also transmits real-time data, maintaining a communication line between remote marine-based equipment and the shore. This third-generation wave energy converter is modular by design and adaptable to suit various project needs. Orbital 2. After marveling at the American innovation, let's cross the Atlantic to the chilly waters off Scotland's Orkney Islands. There resides the world's most potent tidal turbine, the Orbital 2, built by the Scottish company Orbital Marine Power. This colossal structure stands as tall as a 24-story building and weighs a staggering 680 tons. Yet, despite its size, its environmental footprint is negligible. Emitting zero emissions, it presents a tangible step away from fossil fuels. The Orbital 2 magic lies in its bidirectional operation, generating electricity both high and low tides, increasing its efficiency significantly. This powerhouse, launched in July 2021, promises enough electricity annually for 2,000 households, harnessing the power of the sea to light up our homes. Gents, isn't it amazing how renewable energy is reshaping our world? Wave Star Machine. Sailing ahead in our journey, we encounter another fascinating piece of renewable energy tech, the Wave Star Machine. Conceived by a Danish company, Wave Star, this marvel harnesses the rhythm of ocean waves to light up our lives. Imagine a floating energy farm tethered to the seabed with a series of floats that rise and fall with the waves. This motion powers a hydraulic system that drives a generator to be mammals, developed by Swinburne, land of the rising sun. Japan emerges US and Europe with zero emissions. We continue exploring the power in the tides, the waves, and the smallest streams. It's clear our future is renewable. If you're as excited about these advances as I am, don't keep it to yourself. Hit that like button, share this video, and bring.
Yes, I am sharing that slides. Yes, any questions to anybody?
Hello, thank you very much, sir, for a wonderful session. Participants, now you can ask your questions through chat box so that our speaker can clarify your doubt. So before asking one question to all participants that your attendance is mandatory and you should be maintain your 3 hour sessions completely. So make sure that. And you can ask questions now in the chat box. Sir, questions are arrived in the chat box. Just you can look at it.
Yes, any questions are if anybody wants to add more in addition to this, welcome. Because probably you might be knowing latest developments. You can share for benefit of other participants also. Or I am having these coordinators is having my mobile number, email is there, and I will share that in PPT. I will send you for participants. So in case anybody requires more data, I will send you.
Yes, sir. We'll share the all data of all sessions and speakers data through Gmail and professional ID, sir, after the end of the sessions. Sir, one question arrived. May I ask that question for you so that what type of turbines are used in geothermal power plants? Krishna Patar, he asked the question.
Yes, any questions? Anybody?
Sir, it is in chat box, sir. So I will make sure to take that question for you. Krishna Patar asking, sir, what type of turbines are used in geothermal power plants?
Yes.
What type of turbines are used in geothermal power plants?
So in this Kaplan and furnace, 5-6 turbines are used in this geothermal power plants. But in that, we have to take precautions so that no any corrosion or melting of this is there. Just like we are having in thermal power stations, turbines are there. Same heat temperature is there, more than 273 degrees centigrade temperature is there, steam temperature, and we have to take that corrosion problem. Because corrosion is one of the issue in turbines. Failure of turbine blades is the corrosion. Hence, we have to take that protective cover, protective layer of paints. We have to make that. Because very hot temperature, hot springs temperature, water temperature is there. Hence, we have to take that precaution so that melting or bending of these turbines is not there. Or a whole pipeline and all passage. So these precautions we have to take. Yes, one question from Mr. Vivek is that geothermal energy can be harvested in western region, Ghat region by boring to 1000 feet. Because this region is oldest geothermal. It can be there, but that also depends when Geological Survey of India, GSI, is exploring the potential sites. After that, we can install that. Because if hot rock is there or some water springs are there, but this is not only the one factor. Another parallel affecting factors are also there, in which no means community should be disturbed or a locality of that people should not be displaced, and plus it should be ensured throughout year. This is one of the requirements because this is the base load plant geothermal. Hence, and GSI has explored this, identified these areas, sites. In that, this works is going on. Even now, Leh has been declared the world's first airport where geothermal energy and solar energy both will be used. Means it is totally dependent on renewable energy. And Cochin Airport is totally on solar energy utilization. Different 94 airports have been earmarked on working on these green fuels, means reducing this carbon footprint, carbon emissions. And GSI is exploring this. This is, of course, this Government of India organization, and they are exploring. And after their potential results and all factors considered, then government takes decision to start that project in that, because it is requiring huge infrastructure cost. And moreover, this availability of the fuel, just like hot springs or hot gases, what we can also use in that, just like we are having in geysers in California. These are, it should be ensured. Then only these plants can be commissioned there. Now even AI and machine learning algorithms are also used in this exploration of these hot springs and geothermal sites. Yes, so more topics on solar energy and other area renewable energy I am having, but if time permits, because now time is over. Otherwise, I could have shared that slides, but no problem. In case when an opportunity arises, I will be there.
Thank you very much, sir. Thank you very much for a nice session, sir. It's a wonderful session. So, before going to end the session, all participants, please fill out the feedback form. And thank you very much, sir, for the session. And we can end the session now, sir.
I'm congratulating you for having more than 280 participants. That I am seeing for first time.
Thank you very much, sir.
Yes,
It's a teamwork,
it is more
sir.
thing for you. You have made these people to more than 280 people participants in your training. That is very, means probably it will be your first training in ATAL FDP history, if I am not wrong.
Hope so, sir. Thank you.
Yes, yes. It seems ki you will be the highest participants organization this training, at least this training.
Thank you very much, sir. It means
Yes.
a lot.
Yes. Okay. Thank you.
Thank you very much, sir.
So these PPTs for participants I will share, and questions also. You will be requiring for quiz, na?
Yeah, sir.
I will be sending that within half hour.
Yeah.
You will be getting that.
Yeah, sure, sir. Thank you very much.
Okay. Yes. Thank you. Yes. Should I leave?
Yes, sir.
Thank you. Yes.
And all participants, thank you very much for your patience. We'll join the session tomorrow by the same time, 6 o'clock. So, by that time, signing off. Have a nice time. Please fill the feedback form, all participants. Okay, thank you very much, sir.